Before the first tick of time, the universe didn't sit in darkness. It had nowhere to sit at all. No space, no seconds, no stage beneath reality, just the idea of nothing. So what do physicists mean by nothing? And if time itself began with the Big Bang, how can there be a before to anything? In the beginning, if beginning is even the right word, our universe is not a place but a question. We point to the Big Bang as a starting line, yet the closer we look, the line starts to move. Because before assumes a clock, and a clock assumes time, and time may be part of what began. Tonight we follow the evidence backward, not by imagination, but by light that has been travelling for billions of years. Galaxies lean away in redshift, an expansion written into their spectra like a slow cosmic retreat. The afterglow of the early universe still fills the sky, whispering at 2.7 Kelvin from every direction. And in the first minutes, simple elements formed in ratios that still survive. Quiet arithmetic from a furnace we can no longer touch. These are not myths, and they are not metaphors. They are measurements, repeated, refined, and cross-checked, forming a history we can read with extraordinary confidence. Yet that confidence has an edge, and at the edge the questions become sharper. When we run the equations of space-time backward, density climbs, temperature rises, and the geometry tightens toward a boundary where classical physics cannot promise meaning. The singularity is not a scene we can film, but an alarm bell in the mathematics, warning that our description has failed. So what did nothing mean, if there was ever a before at all? In ordinary life, nothing is an empty room, though the room still swarms with air, heat, and electromagnetic noise. In space, nothing is a cosmic void, though gravity still rules it and fields still pass through. Even our best vacuums are never perfect, because nature refuses to be fully silent, and then physics offers a deeper kind of emptiness, one that looks calm only from far away. The quantum vacuum is the lowest energy state of fields, yet it seethes with fluctuations that can leave measurable fingerprints. It is not philosophical non-being, it is structure without substance, restlessness without a particle. If the early universe was shaped by such fluctuations, then nothing may have been a kind of something, subtle, invisible, and unavoidable. But the ladder descends further. What if the most radical meaning of nothing is not empty space at all, but the absence of space-time itself? No stage, no distance, no duration, no was, because grammar breaks when there is no time to carry it. In that territory, asking what came before can be like asking what lies north of the North Pole. The words still form a question, but the map may not. This documentary is a journey to that boundary, where observation meets inference, and inference meets the limits of language. We will watch the universe expand in reverse, tracing a timeline built from redshift and the geometry of space-time. We will linger in the cosmic microwave background, the oldest light we can see, and listen for the patterns that hint at an earlier prelude. We will confront horizons and singularities, not as dramatic endings, but as signs that a deeper theory is required. Then we will turn to proposals that reshape the opening act without rewriting the evidence. We will explore an early burst of accelerated expansion that could smooth the cosmos while planting the seeds of structure. We will descend into the quantum vacuum, where emptiness acquires properties and where nothing becomes an active player. And we will ask the hardest question with the least comfortable answer. If time is dynamical, can it have an origin? And can origin have a meaning? Along the way, we will test alternatives, bounces, cycles, and collisions across hidden dimensions, without granting them victory in advance. Because in cosmology, the sky is the referee, and every beautiful idea must answer to what the universe actually shows. At the frontier, we reach quantum gravity, where space-time may emerge from something deeper, and where the beginning might be less like a spark and more like a phase change. What you will not find here is a single, final definition of nothing. What you will find is a sequence of increasingly radical meanings, each one stripping away another assumption we did not know we were making. And at the end of that sequence, the central question returns, transformed, no longer only about the universe, but about what it takes for any reality to be possible. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will climb down through layers of nothing, from empty space to quantum vacuum, to the possible absence of space-time itself. And when the word before stops behaving, we will see what modern cosmology can still say with honesty. We begin with a word that feels simple until you press on it: nothing. We use it to name absence, silence, and blank space, then assume the universe must obey that grammar. In ordinary speech, it sounds final, like a door closing, yet in physics it opens into competing definitions. Ask what existed before the Big Bang, and the question lands like common sense. Something must come from something, and time must have been there to host the change. Yet cosmology warns that the word before may smuggle in an assumption the universe does not grant. It may be less a question about history than a question about what counts as a meaningful timeline. In everyday life, nothing usually means an empty room. The lights are off, the shelves are bare, and the air seems irrelevant. But the room is still full of molecules, thermal motion, and electromagnetic noise. Dust drifts through sunbeams, and the faint hum of power lines threads the walls. The walls still define a volume, and time still ticks without asking permission. Even a quiet room is busy at microscopic scales. Air molecules ricochet in chaotic trajectories, and their collisions encode temperature in the plainest sense. Infrared photons leak from warm surfaces, and the floor radiates heat like a slow, invisible tide. When we say nothing is happening, we usually mean nothing we care to notice. Move outward, and nothing becomes the interstellar void. Between stars, matter thins until a cubic centimetre can hold only a few atoms. The darkness feels absolute, but it is threaded with starlight, magnetic fields, and stray particles. Cosmic rays, nuclei accelerated to extreme energies, still punch through the emptiness. Space remains a stage, and the stage still has rules. Visually, that void is not a pure black. It is a velvet field stippled by distant suns, with faint nebular haze and the occasional glint of dust scattering light. Gas clouds stretch for light years, so thin they would shame any laboratory vacuum. Even there, gravity is not absent. It is simply patient, shaping orbits over millions of years. Then physics tightens the meaning again, and nothing becomes a vacuum. Pump a chamber down, cool it, shield it, and remove almost every particle you can. Engineers chase lower pressures with metal seals, cryogenic traps, and careful materials that do not outgas. Yet the vacuum is not a simple blank, and it never becomes a perfect zero. Even a high vacuum keeps a few wanderers. A lone molecule can cross the chamber like a slow comet, and a stray photon can still strike a detector. The more you remove, the more you notice what remains: fields, fluctuations, and the stubborn persistence of energy. In the language of quantum theory, empty space has structure. Fluctuations appear in calculations, and measurable effects follow from that restless ground state. The Casimir effect and vacuum polarization are not metaphors. They are reminders that the vacuum is a physical medium described by equations. Put two conducting plates close together, and the allowed modes of the electromagnetic field change. Pressure appears where intuition expects nothing. Vacuum polarization adds another layer. In quantum electrodynamics, the vacuum behaves as though it can briefly screen electric charge, altering forces at very small distances. The details live in precise mathematics, but the plain language point is simple. Empty, in quantum physics, still has properties that can be measured. So when someone says the universe came from nothing, which nothing do they mean? An empty room still has space and time. A near-perfect vacuum still has quantum fields. None of these are the radical absence people imagine when they picture nothing at all. That imagine nothing is closer to a total lack of arena, law, and possibility. Cosmology pushes toward a deeper edge. The most extreme nothing would be the absence of space-time itself. No distances, no durations, no background arena where events could occur. If space-time is missing, then even the question of what happened becomes unstable. Cause and effect depend on time, and time is part of what would be absent. This is where language starts to fight the physics. The word before implies an earlier moment on a timeline. It assumes time is a container that exists independently of what fills it. But general relativity treats time as part of space-time, and space-time can evolve. In Einstein's picture, geometry is not scenery. It is a dynamical actor. Historically, that shift was hard-won. Newton's universe offered absolute time, flowing the same everywhere, whether or not anything changed. Einstein replaced that with a fabric whose measurements depend on motion and gravity, and whose curvature responds to energy and pressure. It is a conceptual trade. you lose a universal clock and you gain a theory that predicts new phenomena. The Big Bang model is often misunderstood as an explosion in pre-existing space. That picture is intuitive, and it is wrong in the way that matters here. The model describes space itself expanding, carrying matter and radiation with it. It is not a blast travelling outward into emptiness. There is no outer wall the shockwave is racing toward. A better visual is a grid being stretched. Galaxies are not shrapnel thrown into a void, they are markers embedded in the grid, separating as the grid expands. On large scales, every observer sees others receding, and no special centre appears. The expansion is a property of the metric, the way distances are defined. In that framework, the early universe is not a point in a room. It is a state where distances between all co-moving points were smaller, temperatures were higher, and densities were greater. The equations run backward toward a hot, dense beginning. They do not point to a centre in space. They point to a limit in time, where our description strains. When people ask what came before, they may be asking for a cause. They may be asking for a previous state. Or they may be asking whether the beginning is a boundary, where the concept of earlier stops applying. These are different questions wearing the same sentence. Each one demands a different kind of answer, and some may have none. General relativity allows a startling possibility. Time, as we measure it, may have a finite past. If the Big Bang is the boundary of space-time, then there is no earlier time in the same way there is no point north of the North Pole. The phrase sounds evasive, yet it is a precise claim about coordinates and geometry. It says the map ends because the surface ends, not because we forgot to draw. Still, we cannot settle this by wordplay alone. The Big Bang is not a philosophical slogan, and it is not a single event we witness directly. It is a model built to explain observations that converge on the same story. The story says the universe was once hotter, denser, and more uniform. It also says that the evidence is written into the sky, if we know how to read it. The first pillar is the expansion discovered in the galaxies. In the early 20th century, astronomers debated whether spiral nebulae were nearby clouds or distant island universes. When their distances were established, the scale of the cosmos snapped into focus. Then Edwin Hubble and others found a pattern. Distant galaxies show redshift, and the redshift grows with distance in a systematic way. Redshift is not just a colour shift in a rainbow. It is a stretching of wavelength, a change in the spacing between wave crests as light travels through expanding space. The simplest reading is that space has been stretching, and light has been stretched with it. Run that expansion backward, and the universe contracts toward an earlier compact state. The farther we look, the more we look into the past. The second pillar is the cosmic microwave background. It is faint radiation arriving from every direction with extraordinary uniformity. It carries the spectrum of a cooled thermal glow, like embers after a fire. That glow is the afterimage of a time when the universe was hot enough for matter and light to stay coupled. It is also a time capsule, because it has been travelling to us for nearly the age of the cosmos. To picture it, imagine the entire sky as a screen. Every direction is a different line of sight, yet the CMB arrives with almost the same temperature everywhere. The uniformity is not perfect, and that imperfection is the point. The CMB is the oldest light we can see directly, because earlier than that the universe was opaque, like fog before it thins. The CMB is not perfectly smooth, and that matters. Tiny temperature variations map small density differences in the early universe. Those differences later grew into galaxies and clusters under gravity. The pattern is a fossil record, and it lets us test the model with numbers. It is also a portrait of primordial conditions captured when the universe first became transparent. The third pillar is the abundance of light elements. Hydrogen and helium dominate, with traces of deuterium and lithium in specific proportions. Those ratios match calculations of nuclear reactions in a young universe that was hot and dense for minutes. In that brief window, protons and neutrons assembled into the first nuclei, long before stars existed to forge heavier elements. The agreement is not exact in every detail, but it is strong enough to anchor the basic timeline. Together, these clues do not prove a creation from nothing. They establish that our observable universe emerged from an early hot, dense phase and has been expanding and cooling since. They tell us that the Big Bang model is a description of evolution, not a claim about an ultimate origin. The model is powerful because it predicts multiple, independent signatures that converge, yet the model has a limit, and the limit is where our central mystery lives. If we push the equations back far enough, densities rise and curvatures grow. Eventually the math points to a regime where quantum effects of gravity should matter. We do not yet have a complete tested theory for that regime. Our best equations begin to disagree, not because nature is inconsistent, but because our tools are incomplete. That boundary is often described with the word singularity, but the word can mislead. In many contexts it signals that a model has reached the edge of its applicability, like a thermometer that cannot read beyond its scale. It may represent a real physical feature, or it may represent a missing piece of theory. Either way, it marks a place where confident narration must slow down. At that boundary, two temptations appear. One is to declare that physics ends and metaphysics begins. The other is to pretend the equations can be trusted past their domain. The honest move is to mark the edge clearly, then ask what new principles could extend the story. In science, humility is not surrender, it is a method. This chapter is about that edge of meaning. It is about how a single word can hide multiple physical claims. It is about how the universe can have a beginning in time without requiring a moment before it. And it is about how evidence can be solid while the deepest interpretation remains open. The mystery is not a gap in data alone, but a tension between concepts. We will keep three labels in view as we go. Known will mean supported directly by observation and well-tested theory. Inferred will mean strongly suggested by models that fit the data. Unknown will mean the region where several ideas compete, and no experiment has yet chosen a winner. These labels are not decorations, they are guardrails. The question of nothingness sits across all three categories. The vacuum is known to be active, yet its full role in cosmology is still inferred. The absence of space-time is a concept we can name, but we do not know whether nature ever realizes it. And the word before may be meaningful in some theories and meaningless in others. The same syllables can point to radically different claims. So we return to the hook, now sharpened. Before the first heartbeat of time, before space could stretch or light could travel, what could it even mean to ask what was there? When you remove time, you remove the stage for was, and the grammar begins to wobble. Yet the mind insists on asking, because causality is how we make sense of change. If time begins with the Big Bang, then the question may be like asking what lies beyond the edge of the map. The map is not hiding a secret continent, it is showing the boundary of what the coordinate system can describe. But if time is emergent, or if the beginning is a transition, then a deeper story may exist. The difference is subtle, and it matters. The path forward is not to choose an answer by taste. It is to descend step by step from familiar emptiness to the most radical form of nothing. It is to learn what the Big Bang model actually says, where it is confirmed and where it stops speaking. Then we can ask which proposed extensions preserve meaning, and which merely rename our ignorance. The goal is not comfort, but clarity. Next, we follow the universe backward toward the earliest times we can describe with confidence. We watch the hot plasma cool, we track when atoms form, and we see how the CMB becomes a messenger. At the end of that trail, we meet the first hard boundary, and the word nothing changes again. Chapter 1 warned that before can smuggle in a hidden timeline, as if time were an external stage. Chapter 2 builds the timeline we can justify with measurements, then shows where that timeline frays at the edges. Cosmology begins with a simple claim that can be checked against the sky. On the larger scales, the universe is expanding, and that expansion leaves a measurable signature in the light itself. The signature is redshift. Light from distant galaxies arrives stretched, with wavelengths longer than when they were emitted, and the shift can be read directly from spectral lines. In practice, astronomers compare a galaxy's spectrum to laboratory fingerprints of atoms and ions. The lines appear displaced toward longer wavelengths, an orderly slide, not a blur, which lets redshift be measured with striking precision. At first glance, redshift sounds like ordinary motion, and that instinct is not wrong. A source moves away, waves spread out, and the colour shifts toward red in the familiar Doppler picture. That Doppler mechanism is real in many settings, from sirens to binary stars, and it remains useful nearby. But cosmology adds a deeper mechanism. Space itself expands, and it stretches the light while it travels. The distinction matters because it changes the story we tell about the past. We are not tracking debris flying through a static arena. We are tracking an arena whose ruler changes while the race is underway. Visually, imagine a grid drawn on rubber, with galaxies pinned to the intersections. The galaxies can sit still on the grid, yet the grid expands and their separations grow without any central explosion point. The observational backbone is the Hubble, Lemaitre law. The farther a galaxy is, the faster its recession appears, in a near-linear relationship that emerges when we average over local gravitational clutter. Historically, the pattern was assembled from multiple minds and imperfect data. Vesto Slipher measured galaxy redshifts early. Georges Lemaitre connected them to an expanding solution of Einstein's equations, and Edwin Hubble tied redshift to distance with Cepheid-calibrated galaxies. In modern terms, recession speed is proportional to distance, with a constant of proportionality called the Hubble parameter. Its value changes with cosmic time, so the Hubble constant is really today's snapshot of a living quantity. The law is not merely a fact about galaxies, as if they were special objects with special motions. It is a clue about the geometry of space-time and about how distances evolve between co-moving points that share the cosmic flow. Distance in cosmology is subtle because the universe is not static, and light does not travel through an unchanging stage. We infer distance using brightness, standard candles, standard rulers, and a chain of calibrated steps that must be cross-checked for hidden biases. A standard candle is an object whose intrinsic luminosity can be inferred, so its dimness reveals distance. Type Ia supernovae play this role at great ranges, while Cepheid variables and other rungs anchor the ladder closer to home. A standard ruler is a known physical scale imprinted in matter or radiation. In the large-scale distribution of galaxies, baryon acoustic oscillations provide such a ruler, a faint ripple from early universe sound waves stretched across billions of light years. Once distance is in hand, redshift becomes a clock. Higher redshift means we see the object when the universe was younger, because the photons left earlier and travelled through more expansion. This is the first sense in which redshift becomes a time machine. Looking far away is looking back, because light takes time to cross expanding space, and every telescope is also a historical instrument. But the time machine has a built-in complication that can't be ignored. The universe expands while the light is en route, so the travel time depends on the expansion history, not just the distance today. Cosmologists encode that history in the scale factor AT. It is a single function that tells how cosmic distances grow or shrink with time, and it becomes the master dial for the entire narrative. By convention, AT equals 1 today, which makes the present our reference point. Earlier times have smaller AT, and future times have larger AT if expansion continues, so the same symbol quietly carries past and fate. Redshift links directly to the scale factor in a way that is both elegant and unforgiving. For light travelling freely, the observed wavelength stretches in proportion to the growth of AT, as if the wave were painted on the expanding grid. In compressed form, 1 plus redshift equals today's scale factor, divided by the scale factor at emission. The equation turns spectra into a record of expansion, and it lets a single number, z, summarize an enormous span of cosmic change. This is where expansion of space stops being a metaphor and becomes a statement about the metric. The metric is the rule that converts coordinates into measured distances, and in relativity it is the object that carries gravity itself. In general relativity, the metric is dynamical rather than fixed like graph paper. Matter and radiation influence geometry, and geometry influences how matter and radiation move, so the universe is a coupled system rather than a container. So we need a model for the large-scale metric, one that matches the sky without tracking every galaxy. The simplest successful one assumes homogeneity and isotropy, meaning the universe looks roughly the same everywhere on large scales and in every direction. This assumption is not a claim that the universe is perfectly smooth, because it clearly is not. It is a claim about scale. Zoom out far enough, beyond clusters and voids, and the roughness averages into a near-uniform cosmic backdrop. That assumption leads to the Friedman-Lemaitre-Robertson-Walker metric. It describes an expanding or contracting universe with a scale factor and a curvature label, and it provides the stage on which redshift becomes a geometric consequence. Curvature here is not a local bump like a hill on Earth that you can walk around. It is a global property of spatial slices, describing whether space is flat, open, or closed when you measure triangles and compare their angles. A flat universe makes triangles add to 180 degrees in the large-scale limit, like Euclidean geometry. A closed universe makes angles sum to more than 180, while an open universe makes them sum to less, and the difference becomes a cosmic clue. From that metric and Einstein's equations come the Friedmann equations. They are the core bookkeeping rules for cosmic expansion, translating the contents of the universe into the behavior of AT. Conceptually, the first Friedmann equation links expansion rate to energy density and curvature. It says h squared is set by what the universe contains and how space is shaped, so expansion is not arbitrary, it is constrained. The second Friedmann equation links acceleration to energy density plus pressure. It explains why radiation, matter, and dark energy push expansion differently, because pressure gravitates in relativity, even when it feels like a purely thermodynamic concept. We do not need the full algebra to feel the tension that drives the rewind. If density is higher, expansion changes faster, and running the clock backward makes density rise, which in turn makes expansion evolve even more dramatically. The equations also show that different components dilute differently as the universe grows. Matter thins as volume grows, while radiation thins and also loses energy to redshift, so radiation fades faster than matter as AT increases. This makes the early universe radiation dominated, and the phrase has a precise meaning. Go back far enough, and radiation energy density overwhelms matter, driving a hotter, faster evolving cosmos in which pressure and light are dynamically important. Now the narrative rewinds with structure. We start in a universe of galaxies and clusters, then step backward through eras defined by temperature and transparency, as if we were peeling layers from a cosmic fossil. At late times, gravity gathers matter into galaxies, and galaxies into clusters threaded by dark matter scaffolding. Stars ignite, heavy elements form in stellar cores and supernovae, and light fills space with a complex background of radiation and dust glow. On screen, the modern universe is a tapestry of filaments and voids, with bright knots where galaxies crowd together. The camera can drift through a cluster, past hot X-ray gas, then pull back until the structure becomes a faint web. Rewind further, and the universe becomes smoother, because structure has less time to grow. Galaxies unform into diffuse gas, and the average density climbs as AT shrinks, while the contrast between dense and empty regions softens. Temperature rises as we go back because the cosmic radiation field blue shifts. The same photons that are microwaves today were once infrared, then visible, then ultraviolet, and their energy increases simply because the universe was smaller. This is the thermal history in reverse, and it is more than a poetic image. Expansion cools the universe, so contraction heats it, and the thermometer is written into the spectrum of relic radiation that still bathes every direction. A key milestone is recombination, a deceptively gentle word for a dramatic transition. At about a few thousand Kelvin, electrons combine with nuclei to form neutral atoms, and the universe changes from a fog to a transparent sky. Before recombination, the universe is ionized plasma, a sea of charged particles and photons. Free electrons scatter photons efficiently through Thomson scattering, making the cosmos opaque like a glowing fog in which light cannot travel far. After recombination, photons stream freely because neutral atoms scatter them far less. That released radiation is observed today as the cosmic microwave background, cooled by expansion to only a few Kelvin, yet still astonishingly uniform. The CMB is not only a relic light source like an old photograph, it is a timestamp, an all-sky afterimage, marking the moment the universe became transparent to its own radiation when the cosmic horizon first opened. In redshift terms, recombination sits around Z of about 1100. That number is a compressed way to say the universe was roughly 1,000 times smaller in scale factor, and the average density was correspondingly far higher. The CMB also anchors the model's geometry in a way that feels almost uncanny. Its tiny anisotropies encode the acoustic physics of the early plasma and the curvature of space, because sound waves left a measurable imprint on the sky. Those anisotropies are not decorative noise sprinkled on an otherwise smooth map. They are a quantitative fossil, letting us infer the composition of the universe and the shape of its expansion history with statistical rigor. Visually, the CMB appears as a mottled sphere, with temperature variations of only tens of microkelvin. Yet those faint speckles correspond to density variations that later become galaxies, so the map is both subtle and prophetic. Rewind further and atoms cannot exist for long. Photons are energetic enough to ionize any neutral hydrogen, and matter remains a coupled plasma of nuclei, electrons and radiation, with frequent interactions enforcing near-thermal equilibrium. In that plasma era, pressure matters in a way that modern galaxies no longer reveal. Radiation pressure resists gravitational collapse, and sound waves propagate through the hot mixture, compressing and rarefying matter like ripples in a luminous fluid. The Friedmann equations and plasma physics together predict a hot Big Bang, and the phrase is often misunderstood. It is not a claim about a bang in space. It is a claim about temperature and density, and about how those quantities evolve. Hot means thermal equilibrium held early on, because collisions and scattering were frequent. Dense means interactions were common enough to keep matter and radiation tightly coupled, so the universe behaved like a single, evolving thermodynamic system. This is the part of the story where cosmology is strongest, not weakest, because it is over-constrained. Multiple observations converge on the same thermal timeline, even when measured by different instruments and methods that share few assumptions. Redshift surveys map expansion across billions of light-years, tracing how galaxies populate the cosmic web. The CMB maps the plasma epoch, and its angular patterns act like a ruler laid across the early universe. Light element abundances map the first minutes of nuclear reactions, and they do so with chemical evidence. When we measure helium in pristine gas clouds, or deuterium in distant absorption systems, we are reading a cosmic ledger written before stars. Those abundances come from Big Bang nucleosynthesis. When the universe was seconds to minutes old, temperatures allowed protons and neutrons to fuse into light nuclei, and the competition between reaction rates and expansion froze the outcomes in place. As expansion continued, the universe cooled too quickly for heavier elements to form in bulk. That is why hydrogen and helium dominate, and why heavier elements require stars, where gravity can compress matter and keep fusion going for long periods. Each of these pillars is a different way to read the same underlying function AT, and that unity is the quiet triumph. They cross-check one another, and they constrain the expansion rate at different times, leaving less room for convenient storytelling. But the rewind does not stop at recombination or nuclear synthesis, because the equations themselves do not stop. The Friedmann framework invites us to go further back, into regimes we cannot observe directly, where our evidence becomes indirect and our confidence becomes conditional. As we extrapolate, the scale factor shrinks towards zero, at least in the simplest solutions. Density and temperature soar, and the curvature terms in the equations grow large, so the mathematics begins to point toward an extreme boundary. This is where the documentary's central question sharpens into something almost philosophical. If the model points toward a beginning, what does it mean to ask what came before it, when before is defined by the very time we're extrapolating? For now, we stay disciplined and separate two ideas that are often blended in casual speech. There is the observationally supported hot, dense past, and there is the ultimate origin of space-time itself, which may not be accessible to the same tools. General relativity, applied to an expanding universe, often predicts a singularity in the past. In that limit, quantities like density and curvature diverge, and the scale factor approaches zero in finite proper time along many trajectories. A singularity is not automatically a real object in nature, like a point you could reach with a spacecraft. It can be a warning light that the theory has been pushed beyond its domain, where the equations still run but the meaning drains away. Physics has seen this pattern before, and the lesson is sobering. Classical mechanics breaks at atomic scales, and classical electromagnetism breaks without quantum rules for radiation and matter, so a successful theory can still have a boundary. In cosmology, the suspected missing ingredient is quantum gravity, because geometry itself should become quantum. Near the earliest times, space-time curvature becomes so extreme that quantum effects of geometry should matter, and the smooth metric may no longer be a valid approximation. We do not yet have a complete, experimentally confirmed theory of quantum gravity, and that absence is not a minor technicality. It means our rewind is reliable only up to a boundary of confidence, beyond which we are extrapolating more than we are explaining. The boundary is sometimes placed near the Planck time, when characteristic energies and curvatures reach a scale where quantum fluctuations of space-time are expected. It is not a precise wall, but it marks where our known equations stop being trustworthy guides. So the cliffhanger forms naturally. The same expansion story that explains redshift and the CMB also drives us toward a point where our language and math both strain, as if the narrative were approaching the edge of its own map. If time is part of the dynamical geometry, then before may not be a location we can reach by extrapolation. It may be a category error, not a missing chapter, because the coordinate we are trying to extend might lose meaning. Yet the human mind keeps asking, because causality feels compulsory and deeply wired. If there was a hot, dense state, what set it up? And what does set up mean without time as a background parameter? To keep the mystery honest, we name what this chapter has established and what it has not. We can trace the universe backward through well-tested epochs using redshift, AT, and the Friedman framework, and we can do so with multiple independent checks. We can describe a hot plasma universe, a recombination event that releases the CMB, and a nucleosynthesis era that fixes light element ratios. We can connect those epochs to a coherent expansion history, and we can show how the same equations knit them together. We can also see the limit, and it is not merely a limitation of our telescopes. Extrapolation points toward a singular beginning, and singularities often signal that a theory is incomplete, because infinities are usually symptoms rather than destinations. That incompleteness is not a failure of observation, and it is not a reason to discard the successes. It is a sign that the concept of nothing before the Big Bang might involve more than empty space, because emptiness is still a kind of something. The ladder of meanings from Chapter 1 returns in a new form, and it tightens the suspense. The nothing we approach here is not a vacuum inside space-time, but the possible edge of space-time itself, an edge we can gesture toward, but not yet cross. Next, we follow the rewind closer to that edge. We ask what inflation, quantum fields, and quantum geometry might add, and what they cannot yet prove, as the timeline we built begins to blur into the unknown. We have rewound the universe to a time before stars, before galaxies, before any clear line of sight, when even empty space was crowded with light. The sky still holds a message from that era, and it arrives as a whisper of microwaves, faint, steady, and everywhere at once. The cosmic microwave background is not a metaphor for the early universe, and it is not an artist's reconstruction. It is radiation we measure directly, coming from every direction, with almost the same temperature, as though the cosmos kept a receipt from its first hot phase. When instruments scan the sky, they do not find a patchwork of unrelated sources. They find a single, nearly uniform bath of photons that wraps around us like a spherical shell. This light is old because the universe was once opaque, and then it became transparent, as decisively as fog lifting from a valley. The moment of release is a physical transition, not a poetic boundary, and it is anchored in atomic physics. Before that transition, the universe was not dark in the way a night sky is dark. It was bright in every direction, yet that brightness could not travel. Early on, matter was a plasma of electrons and nuclei, mixed with an ocean of photons, all jostling in relentless thermal contact. Photons scattered off free electrons constantly, so light could not travel far, and the mean free path was tiny compared with cosmic distances. In practical terms, the universe behaved like the interior of a star, except it was the entire universe. In that plasma, temperature and density were high enough to keep atoms from staying intact, even when they briefly formed. Any neutral hydrogen that appeared was quickly ionized by energetic photons, because the photon bath contained many quanta above the 13.6 electron volt binding threshold. The balance was not a matter of a few unlucky collisions. It was a statistical certainty set by the thermal distribution. Expansion cooled the plasma, and cooling changed the balance between ionization and neutrality, because fewer photons remained energetic enough to tear atoms apart. At roughly 380,000 years after the Big Bang, electrons began binding to nuclei in large numbers, and the chemistry of the cosmos finally shifted. The key is not that the universe suddenly made atoms in one instant. It is that the odds tipped, and the plasma could no longer keep everything ionized. This is recombination, though it is really the first stable combination of electrons with protons, and helium nuclei as well. Neutral atoms formed in bulk, and the scattering rate dropped sharply, because neutral hydrogen does not offer free electrons as easy targets. The process is sometimes described as a cosmic phase change, less like a switch, more like a rapid thaw into transparency. Over a relatively narrow span of redshift, the universe changed its optical character. With far fewer free electrons, photons stopped bouncing around like light in fog, and their paths lengthened dramatically. They decoupled from matter and began streaming freely through expanding space, carrying with them the conditions of the moment they last interacted. Those photons did not need new engines to keep shining. They simply kept moving, and the universe kept stretching beneath them. That decoupling defines the surface of last scattering, a shell in our past light cone, and it is one of cosmology's most important geometric ideas. We do not see earlier directly because earlier light was trapped and reprocessed, repeatedly scattered until it forgot where it came from. The last scattering surface is therefore not a wall in space. It is a time slice we intercept in every direction. The CMB is therefore a horizon in practice set by plasma physics and expansion, rather than by any limit of imagination. It is not the beginning of the universe, yet it is the beginning of transparent history. The first moment when information could travel largely unimpeded. When we look at the microwave sky, we are looking at the universe's first long-distance message. Today, that released radiation has cooled to about 2.7 Kelvin, because expansion stretched its wavelengths like taffy pulled across cosmic time. The same photons were once infrared, then visible, then far hotter still, when the universe glowed like a furnace. Redshift did not dim them by exhaustion. It diluted their energy by stretching space itself. The most striking fact is the spectrum, which is almost a perfect blackbody, as though nature ran an ideal laboratory experiment on the grandest possible scale. A blackbody curve is what you get when matter and radiation share thermal equilibrium, so the distribution of photon energies depends only on temperature. It is a smooth, specific shape, and it leaves little room for improvisation. That near perfection implies the early universe was hot, dense, and well mixed, because only frequent interactions can erase distortions. Interactions were common enough to wipe away memory of detailed initial conditions, leaving behind a simple thermodynamic signature. In plain language, the early universe had time to settle into a uniform heat bath. This is one reason the Hot Big Bang is not a guess built from a single clue, or a story told because it sounds dramatic. The CMB spectrum is a thermodynamic fingerprint, and it is extraordinarily hard to fake without a genuine early thermal state. Historically, that realization sharpened in the mid-20th century, when theory predicted an afterglow and observation unexpectedly found it. The discovery by Penzias and Wilson, first heard as stubborn noise in an antenna, turned a speculative prediction into a measurable sky. Yet the CMB is not perfectly uniform, and the imperfections carry the deeper story, like faint ripples on a glassy sea. Temperature varies across the sky at roughly 1 part in 100,000, so the differences are real but exquisitely small. If the average CMB temperature is 2.7 Kelvin, the variations are tens of microkelvin, far below anything our skin could sense. Those anisotropies are tiny in amplitude, but they are huge in consequence because gravity can amplify small beginnings. They mark slight differences in density and gravitational potential in the young universe, places where matter was a little more crowded or a little more rarefied. In the CMB map, those differences appear as mottled, hot and cold spots. The colours are not literal heat you could feel. They are a visual code for minute shifts in photon energy. Gravity later amplified those differences, turning small overdensities into the scaffolding of galaxies and clusters, and turning underdensities into cosmic voids. The CMB is a map of seeds before the forest grew, a snapshot of the soil before the first trunks rose. When we compare that early pattern to today's web of galaxies, we are comparing blueprint to architecture. To understand the pattern, we return to the plasma before decoupling, when photons and baryons were tightly coupled, behaving like a single fluid with pressure. Baryons are ordinary matter, protons and neutrons, while photons supply the pressure through their relentless momentum. In that coupled fluid, disturbances did not just sit still, they propagated. Gravity tried to compress denser regions while radiation pressure pushed back, and the competition produced motion rather than collapse. The result was oscillation, like sound waves moving through a hot glowing medium, except the sound was a compression wave in a plasma. These waves were not heard, but they were real physical vibrations of density and temperature. In a sense, the early universe had a soundtrack written in pressure and gravity. These are acoustic oscillations in the primordial plasma, driven by the tug of gravity and the spring of pressure, and damped by diffusion and imperfect coupling. They left a frozen imprint when photons decoupled, because the photons carried away the temperature pattern at that moment. After decoupling, the waves in the photon-baryon fluid could no longer keep the photons in step. The light escaped, and the pattern stopped evolving in the same way. That imprint appears as peaks in the CMB power spectrum, a statistical summary of hot and cold spots across different angular scales. The peaks are not arbitrary bumps, but a measured harmonic pattern, like overtones in a musical instrument. Each peak corresponds to modes that had time to complete a certain fraction of an oscillation by the time of last scattering. The spectrum is therefore a timing record as well as a temperature record. The first peak corresponds to a fundamental scale, set by how far sound could travel before decoupling, given the plasma's sound speed. It is a standard ruler embedded in the sky, and it is astonishingly useful because it depends on well-understood microphysics. The sound horizon is not guessed from late-time galaxies. It is computed from the early universe's composition and expansion rate. The spacing and heights of the peaks encode the universe's ingredients, because different components change the oscillations in distinct ways. Baryons add inertia to the fluid, dark matter deepens the gravitational wells, and radiation sets the pressure that resists compression. Even neutrinos, light and elusive, subtly affect the pattern by changing the expansion rate and the way perturbations evolve. The CMB is therefore not a single measurement. It is a densely packed bundle of constraints. Baryons change the relative heights of odd and even peaks, because compressions and rarefactions respond differently when normal matter is present. When baryons are abundant, compressions become more pronounced, which boosts certain peaks relative to others. This is how the CMB measures baryon density, not by counting atoms directly, but by reading their dynamical influence. It is a cosmic weighing scale hidden inside a ripple pattern. Dark matter does not couple to photons, yet it shapes the oscillations by providing gravitational potential without pressure support, like invisible scaffolding. Because it can clump without being pushed around by radiation pressure, it begins building wells earlier, guiding baryons once the photons let go. The peak pattern therefore reveals the dark matter fraction, even though dark matter itself never emits the light we are measuring. It is inferred by its gravitational handwriting. The same data also constrain the geometry of space, because geometry controls how physical sizes project into angles on the sky. Curvature changes how a fixed physical scale projects onto angles, shifting where the first peak appears, much like a lens changes the apparent size of an object. When we measure that peak location, the result points to curvature very close to zero. Space on large scales appears nearly flat, within tight observational limits. Flatness here is not a philosophical preference for simplicity, and it is not a claim that the universe must be infinite. It is a quantitative statement about triangles and angles inferred from a ruler laid across the early universe. In curved space, the same ruler would subtend a different angle. The CMB tells us, with remarkable precision, that the angle matches the expectation for near-Euclidean geometry. The CMB also helps determine the age of the universe, because the peak pattern depends on the expansion history, which sets distances and timescales. Fit the model to the spectrum and the timeline becomes constrained, including how long the universe spent in radiation domination, and then matter domination. The result is not simply a number pulled from one dataset. It is a number that must satisfy many interlocking features of the spectrum. This is why the CMB is more than an old photograph, even though it is often described that way. It is a calibration tool that locks together expansion rate, matter content, and the time since the hot dense phase, and it does so with internal consistency checks. The CMB does not merely show us what the universe looked like. It tells us how the universe had to behave to look that way. The analysis depends on a cosmological model, but the model is not free to wander, because the data are structured and demanding. Independent measurements from supernovae, galaxy clustering, and light element abundances cross-check the same parameters, tightening the net around the allowed values. Big Bang nucleosynthesis, for example, predicts helium and deuterium abundances that depend on baryon density. The CMB reads that density in a different language, and the two stories largely agree. Even so, the CMB carries its own internal redundancy, because many multipoles and peaks must agree with one another. The map is noisy in detail, yet the statistics are unforgiving, and small changes in parameters shift the spectrum in recognizable ways. Observationally, the story is also one of improving instruments. Satellites like COBE first established the blackbody spectrum and detected anisotropies, then WMAP refined the map, and Planck sharpened it into a high-definition cosmological dataset. We should be clear about what is being inferred from what, because the chain of reasoning is part of the drama. We measure the microwave sky and its spectrum directly, then infer early universe conditions through well-tested physics, including radiative transfer and gravitational instability. The inference is not mystical. It is the same logic used in stellar atmospheres, applied at a cosmic scale. Thomson scattering, atomic energy levels, and gravitational dynamics are not speculative add-ons, and they are not tuned to rescue a preferred narrative. They are laboratory-tested rules applied to a cosmic setting, where the densities and temperatures were extreme, but still within the domain of known interactions. The hydrogen binding energy is measured in the lab. The electron's charge is measured in the lab. The universe simply used those constants in public. The CMB also carries secondary effects that sharpen the picture, because the photons did not travel through empty passive space. Gravitational redshifts, lensing by intervening matter, and reionization by early stars slightly modify the signal, adding subtle fingerprints on top of the primordial pattern. The integrated Sachs, Wolf effect for instance, links large-scale temperature shifts to evolving gravitational potentials. Lensing gently smears and distorts the anisotropy pattern, converting some of its structure into new statistical features. Those modifications are not nuisances alone, because they provide extra information if we know how to read them. Lensing traces the distribution of matter, including dark matter, along the photon's path, and it connects the CMB to the later cosmic web. Reionization reveals when the first luminous structures formed, because ultraviolet light from early stars and galaxies reionized hydrogen, reintroducing free electrons that scatter CMB photons again. That later scattering does not erase the CMB, but it slightly damps small-scale anisotropies and imprints polarization signatures. Still, the core message remains anchored at decoupling, around redshift 1100, when the universe was young and dense. The universe was about 1,000 times smaller in scale factor than it is today, so distances were compressed and temperatures were high. In a visualization, this is the moment when the fog thins and the horizon suddenly expands. The last scattering surface becomes a luminous sphere around the observer, no matter where the observer is placed. At that time, the cosmos was remarkably uniform, but not perfectly so, and the imperfections are structured rather than arbitrary. The anisotropies show a specific statistical character that is as important as their amplitude, because statistics carry clues about origin. The pattern is not a set of isolated blobs, it is a field with correlations across angles, and those correlations are what the power spectrum captures. The fluctuations are close to Gaussian, meaning they look like random noise with a well-defined power spectrum, rather than sharp spikes or rare dominant features. That simplicity suggests an early mechanism that generated perturbations broadly and cleanly, without introducing strong non-Gaussian signatures. In plain terms, the universe's initial roughness looks like the outcome of many small independent contributions. It looks like a process that was simple in its rules, even if profound in its implications. More striking is the near-scale invariance of the spectrum, because it hints that no single length scale dominated the creation of the perturbations. Roughly speaking, fluctuations have similar strength across a wide range of length scales when expressed in the right variables. This is not what you would automatically expect from a messy, late-time causal process. It looks like a pattern stretched across scales with deliberate uniformity. Scale invariance is not demanded by recombination physics, which only freezes what already exists, like a camera shutter capturing motion mid-step. It points backward, toward an earlier process that set the initial pattern, before the plasma began its acoustic ringing. The CMB therefore becomes a messenger from two epochs at once. It speaks clearly about decoupling and indirectly about what came before. This is where the CMB begins to speak about a time we cannot see directly. It becomes evidence not only for the hot plasma, but for whatever prepared the plasma's irregularities, setting the initial conditions for all later structure. The last scattering surface is a limit for photons, not necessarily a limit for inference. We cannot watch earlier light travel, but we can read earlier causes in later patterns. Inflation is the most famous candidate mechanism, and it entered cosmology partly to address puzzles that the CMB makes vivid, It proposes a brief era of accelerated expansion that stretched quantum fluctuations to cosmic sizes, turning microscopic uncertainty into a macroscopic template. In that picture, the universe is smoothed while still retaining tiny ripples, because quantum fields cannot be perfectly still. The ripples then become the seeds we read in the CMB. Inflation also offers an explanation for why the universe looks so flat and so uniform on large scales, even across regions that seem too far apart to have equilibrated in ordinary expansion. Rapid expansion drives curvature toward near zero and dilutes pre-existing gradients, leaving behind a cosmos that is broadly homogeneous. Yet it does not erase everything. It leaves a faint, statistically patterned residue, precisely what the CMB displays. Yet inflation is not the only imaginable mechanism, and the CMB does not hand us a signed confession with a single unmistakable signature. Alternatives can mimic some predictions, and the decisive tests are subtle, often hiding in polarization patterns or tiny deviations from perfect scale invariance. The challenge is not that the data are vague. The challenge is that multiple early universe stories can cast similar shadows. What the CMB does tell us is that the primordial fluctuations were adiabatic to high precision, meaning the different components fluctuated in step. Photons, baryons, and dark matter share the same pattern of over and under density, implying a common origin rather than independent noise sources. That coherence is not a trivial detail. It narrows the space of plausible mechanisms. It also tells us that the fluctuations were coherent in phase, producing sharp acoustic peaks rather than a smeared featureless spectrum. Coherence is hard to arrange with late-time causal processes alone, because the phases must align across regions that were not in contact under ordinary expansion. The peaks are therefore not just decorative. They are evidence that the initial perturbations were laid down in a coordinated way. These features make the early universe feel both simple and unsettling, and that tension is part of the chapter's mood. Simple, because a small set of parameters fits a vast dataset, and because the physics is familiar in its ingredients. Unsettling, because the fit points to physics earlier than our last scattering horizon, where our everyday intuition about time and causality starts to strain. The CMB is a calm surface with a deep current beneath it. We can now connect this back to the documentary's central question about nothing and before, because the CMB is often mistaken for a boundary of existence. The CMB is a wall of light, but it is not a wall of being, and it does not mark creation. It marks when the universe became transparent, not when the universe began, and that distinction matters. A change in opacity is not the same as an origin. Asking what came before decoupling is meaningful, because time and plasma physics still apply there, and because the universe was already evolving in a well-defined way. Before decoupling, the cosmos was hotter, denser, and more tightly coupled, but it was still describable with known interactions. We can model that era with confidence, because the same physics governs laboratory plasmas and atomic transitions. The difficulty is not that the era is unknowable. The difficulty is that it is not directly visible. But asking what came before the earliest moments of the hot, dense phase is different, and it is where language begins to wobble. At some point, our reliable timeline approaches the edge where spacetime itself may be emergent, and where quantum gravity could matter. The CMB does not solve that, it sharpens it. The CMB strengthens the hot Big Bang story while also tightening the noose around the origin mystery, because it confirms a thermal beginning with measurable precision. It confirms a universe that was once in near equilibrium, yet it hints at a prelude that shaped the initial ripples. Those ripples look like they were laid down by a process that operated when the universe was far younger than 380,000 years, long before atoms could survive. The mechanism may involve quantum fields in curved spacetime, or something even deeper, something that treats spacetime as a participant, not merely a stage. If inflation happened, it pushes the question of beginnings back rather than erasing it, and it forces a new set of questions. It replaces one boundary with another, and it forces us to ask what set inflation's conditions, what started it, and what ended it. Was inflation a generic outcome, or a special event with special initial data? And if it was special, what does that say about the word nothing that we keep circling? If inflation did not happen, then another mechanism must explain the same near-scale, invariant, coherent pattern, and it must do so without breaking the constraints the CMB imposes. Either way, the CMB insists that the early universe had structure in its randomness, and that the randomness was disciplined. It is not chaos, It is a particular kind of order disguised as noise. This is the chapter's pivot, and it is why the afterglow feels like both evidence and invitation. It tells us how the universe behaved, and it tells us what we still cannot see, because the most important clues are encoded in what is almost, but not quite, uniform. When the map is shown on screen, the colours can be exaggerated until the sky looks turbulent. Yet the narrator must remember that the true signal is delicate, and the delicacy is the point. We end with a discipline distinction, because clarity is part of the mystery rather than its enemy. The CMB makes the hot dense past a measured reality, and it lets us quantify composition, geometry and age with precision, using physics that can be tested and retested. At the same time, the CMB points beyond itself, toward primordial fluctuations that seem to come from an earlier chapter of physics. That earlier chapter is where the word nothing starts climbing its ladder again, rung by rung, definition by definition. Next, we follow those fluctuations backward, past the last scattering surface, toward the mechanisms that could generate them. The closer we get to the beginning, the more the meaning of before begins to wobble, and the more the universe feels like a question asked in the language of light. We have a timeline that fits the sky, and it still ends in a question. When we run the expansion backward, the universe heats, densifies, and brightens into a compact blinding state, until the mathematics itself begins to blur. That boundary is where the central question sharpens, because our equations keep pointing toward an edge they cannot cross. What does nothing before the Big Bang mean if time itself is part of the system, and not an external clock ticking in the dark? General relativity is our best classical theory of space-time and gravity, and it reshaped physics in the early 20th century. Einstein replaced Newton's invisible pull with a new idea that is at once elegant and unsettling. It does not describe gravity as a force acting inside space. It describes gravity as geometry, and matter tells geometry how to curve, while curved geometry tells matter how to move. In visuals, this is often drawn as a rubber sheet, but the real picture is more severe. Space and time are welded into a four-dimensional fabric, and curvature is not a dent in something larger. Curvature is intrinsic, meaning it is measured from within the fabric itself, using rulers and clocks that are also part of the system. That self-contained quality is why the word before becomes slippery, because the stage and the actors are the same object. In cosmology, we apply relativity to an expanding, nearly homogeneous universe, and we do it with a disciplined set of symmetries. The assumption is not that the universe is perfectly uniform, but that on the larger scales it is statistically smooth. The FLRW metric encodes that symmetry, describing a cosmos that looks the same in every direction and at every location, once you average over galaxies and clusters. From that metric, the Friedmann equations drive the scale factor, the single function that tells us how cosmic distances stretch with time. When we extrapolate those equations backward, the scale factor shrinks towards zero, and familiar distances collapse. Galaxies are no longer islands in blackness, because the blackness itself becomes a hot, luminous plasma. Temperatures rise as wavelengths compress, and the universe becomes a furnace filled with radiation, particles, and relentless scattering. The naive picture says density and curvature blow up at a finite time in the past, and many people call that moment the beginning. But in relativity, the deeper statement is not infinite density, because infinities can be artifacts of pushing a model beyond its domain. The deeper statement is geodesic incompleteness, an austere phrase that carries the weight of an ending. It means that the space-time, as a mathematical object, cannot be extended smoothly along certain paths. The story does not necessarily end with a physical point of infinite matter. It ends because the map of space-time itself stops providing directions. A geodesic is the path a freely falling observer follows through space-time, guided only by gravity. It is the closest thing relativity has to an inertial straight line, except straight now means extremal proper time in curved geometry. Imagine an astronaut drifting with engines off, or a photon slicing across the cosmos, each tracing a world line that geometry defines. If geodesics cannot be extended arbitrarily far into the past, then the space-time is incomplete, even if no one ever reaches a literal edge. That is what the singularity theorems make precise under broad conditions, and their historical impact was immediate. In the 1960s, Roger Penrose and Stephen Hawking showed that singular behaviour is not a fragile coincidence of symmetry. Under reasonable assumptions, such as energy behaving in physically sensible ways, and the universe expanding on average, past-directed geodesics often terminate. The theorem does not prove a physical point of infinite density exists. It proves the classical description runs out of road. The assumptions matter, and they are worth lingering on because they reveal what the theorems actually say. They use conditions that, in plain language, prevent matter from behaving too exotically, like negative energy that cancels gravity's focusing effect. They also rely on the idea that gravity tends to focus families of geodesics, squeezing them together the way a lens squeezes light rays. In an expanding universe traced backward, that focusing becomes a convergence, and the geometry can pinch off in finite proper time. So a cosmological initial singularity is not necessarily a place, and it is not a tiny bead of matter sitting somewhere in space. It is a statement that the model's space-time cannot be continued as a smooth manifold, meaning the coordinate charts and the differentiable structure fail. Time, as measured along many world lines, has a finite past length, and then the notion of earlier stops being defined within the model. The singularity is not inside the universe. It is where the universe, as described by that set of equations, stops being a well-posed object. This matters for the word before, because everyday language smuggles in an external timeline. If time is internal to the geometry, before the beginning is not like earlier pages in a book. It may be like asking what is north of the North Pole, where the grammar makes sense but the coordinate system has ended. The question can be meaningful in language and meaningless in physics, depending on what we mean by time. Still, we should be careful about what singularities are and are not, because popular imagery often misleads. A singularity is not an object sitting inside space-time like a star or a black marble. In general relativity, singularities are typically not part of the manifold at all, which means they are not locations you can point to on a cosmic map. They show up as divergences in curvature, scalars, or energy density, in a coordinate-independent way, and that independence is crucial. Curvature scalars are built from the Riemann curvature tensor, the mathematical object that encodes tidal gravity. If those scalars diverge, it is not merely a bad choice of coordinates, like the fake singularity at the event horizon in old black hole coordinates. It is a sign that tidal forces in the model become unbounded. Yet the divergence is not automatically a real infinity in nature, because nature may refuse to follow the classical script at such extremes. It can be a sign that the theory's assumptions have been violated, or that additional physics becomes dominant. Physics treats infinities as alarms, not as destinations, and the history of science is full of these alarms. When classical electrodynamics predicted the ultraviolet catastrophe, it was not the universe that failed. It was the classical assumption that energy could be shared continuously among modes, and quantum theory replaced the wrong assumptions with discrete quanta. When classical gravity predicts infinite curvature, we suspect a missing quantum description of spacetime because the classical continuum may be the approximation that breaks. Near the putative beginning, energies approach the Planck scale, where our familiar categories start to wobble. The Planck length is unimaginably small, and the Planck time is unimaginably brief, yet the equations suggest that is where curvature becomes extreme. At that scale, quantum fluctuations of fields are unavoidable, and the metric itself should fluctuate, because the gravitational field is the geometry. A smooth classical geometry becomes a questionable approximation, like trying to describe a stormy ocean as a perfectly flat plane. We can picture this visually as the cosmic fabric turning grainy, not because space is literally made of grains in our current theory, but because the continuum description loses predictive power. Quantum uncertainty would not only shake particles and radiation, it would shake the very intervals that define distance and duration, making 1 second earlier a statement that may not have a stable meaning. The closer we push toward that boundary, the more we are forced to admit that our most basic coordinate, time, may be emergent rather than fundamental. We do not yet have a complete tested theory of quantum gravity, and that gap is not a minor technicality. We have candidates and partial frameworks, but not a final, experimentally anchored set of equations that everyone agrees is correct. Some approaches quantize geometry directly, while others embed gravity in a deeper structure, yet none has been confirmed in the way general relativity and quantum field theory have been. So the singularity is best read as a limit of classical general relativity, not as a final statement about reality. This is where the documentary's ladder of nothing returns with sharper edges, because each rung hides structure. Empty space is still a geometry with rules and clocks, and even a perfect vacuum can curve under gravity. A quantum vacuum is still a stage with fields and fluctuations, seething with temporary excitations that can leave measurable traces. The singularity hints that the stage itself may fail, and that nothing is not the right word for what lies at the edge of our models. Now the narrative rewinds with a new tension. The hot Big Bang is a robust description of an early hot dense state, and it is supported by multiple lines of evidence that agree in detail. We see the relic glow of the cosmic microwave background. We measure the abundances of light elements from primordial nuclear synthesis, and we observe the expansion itself in the redshift of galaxies. But the closer we push toward the boundary, the more the meaning of time becomes fragile, as though the timeline is drawn on paper that starts to tear. Even before we reach the Planck regime, the standard Big Bang picture faces puzzles that are not about small discrepancies. These puzzles are not about the last scattering surface itself, which we model with exquisite precision. They are about why the universe at last scattering had the properties we measure, and why those properties are so globally coordinated. In other words, the hot Big Bang describes evolution well, yet it seems to inherit initial conditions that look strangely arranged. The first is the horizon problem, and it begins with causality, the rule that influences propagate at finite speed. In an expanding universe with no special early phase, signals travel at the speed of light, but space itself stretches while they travel. That means there is a maximum distance over which regions can influence each other by a given time, and that distance is not simply age times c. It depends on the entire expansion history. At recombination, the universe is only about 380,000 years old, and it is cooling enough for electrons and protons to bind into neutral hydrogen. Before that moment, photons scatter constantly off free electrons, and the cosmos is an opaque plasma, bright like the interior of a star. When neutral atoms form, the scattering rate drops dramatically, and photons begin to stream freely. Those photons are what we now see as the CMB, stretched into microwaves by billions of years of expansion. Light could not have crossed the entire region that later becomes our observable sky by the time those photons were released. So different patches of the last scattering surface should have been causally disconnected, unable to exchange heat or information. Yet the CMB temperature is uniform to about 1 part in 100,000, a smoothness that is almost eerie when mapped across the whole celestial sphere. That uniformity looks like a system that equilibrated, sharing energy until it reached nearly the same temperature everywhere. But the simple Big Bang expansion gives too little time for that equilibration across the whole sky, and the mismatch is geometric. We can state the problem in the language of horizons, which are boundaries defined by light paths. The particle horizon is the maximum co-moving distance light could have travelled since the beginning, measured in coordinates that expand with the universe. In the simplest radiation and matter-dominated history, that horizon at recombination subtends only a few degrees. So why do regions separated by tens of degrees share nearly the same temperature, as if they were once neighbours? Why do they share the same blackbody spectrum with the same mean value? A spectrum so perfect that it looks thermal to extraordinary precision. If they never exchange signals, why do they look as if they agreed on initial conditions, down to a common baseline that spans the sky? The CMB is not merely uniform, it is uniformly thermal, and that is the sharper edge of the mystery. One response is to say the universe was born uniform, and in a sense that is logically allowed. But that answer shifts the mystery into initial conditions, where the singularity already warns us not to trust classical reasoning. It also raises a deeper question about explanation versus description. A good theory should explain why uniformity is natural, not merely assumed, especially when the uniformity spans regions that appear causally isolated. The second puzzle is the flatness problem, and it is about geometry's stability under cosmic expansion. In the Friedmann equation, spatial curvature competes with energy density, and their relative importance changes as the universe grows. Curvature behaves differently from matter and radiation as the scale factor evolves, which means a small early imbalance can be amplified. As the universe expands in ordinary matter or radiation domination, deviations from flatness tend to grow, not shrink. That means near flatness today implies extreme near flatness in the past, and the numbers become uncomfortably sharp. If the density parameter omega is close to 1 now, It had to be tuned to 1 to extraordinary precision early on, far beyond what intuition expects from generic initial conditions. A tiny mismatch long ago would have ballooned into a wildly curved universe by today, either collapsing quickly or expanding so fast that galaxies struggle to form. The observed near-flat geometry looks improbable under the simplest decelerating expansion. We can express the tension without heavy algebra, but the logic still bites. The expansion rate and density had to be balanced with uncanny accuracy at early times, as though the universe began with a carefully selected setting. Otherwise, the universe would have recollapsed quickly or expanded too fast for structure, leaving no long era for stars, chemistry, and observers. The flatness problem is not that flat space is impossible. It is that flatness is unstable in the standard decelerating expansion, so the universe appears to sit on a knife edge. Historically, these puzzles sharpened as precision cosmology matured, especially when the CMB was measured with increasing clarity. Early hints of a cosmic background were debated for decades, and then its discovery transformed cosmology into a measurement-driven science. As satellites mapped the CMB with finer angular resolution, the uniformity became undeniable, while the tiny anisotropies became a new source of information. Those anisotropies are small ripples, seeds of structure, but they sit on top of an astonishingly level thermal sea. The horizon and flatness problems point in the same direction, and the direction is not merely philosophical. They suggest the early universe underwent a phase that reshaped causal structure and geometry, changing what counts as near and far in the deep past. They suggest a prelude that makes the observed universe less surprising because it dynamically drives uniformity and flatness rather than assuming them. The puzzles feel like fingerprints of an earlier episode, pressed into the cosmos and then stretched across time. This is where before becomes both tempting and dangerous to define, because the word invites a simple extension of the timeline. A prelude could extend the timeline earlier than the hot plasma we have tested, giving the universe more time, or a different kind of time, to smooth itself. But it could also change what we mean by time, distance, and causality, because those concepts depend on the expansion history encoded in the metric. If the metric behaves differently in the prelude, then the causal diagram of the universe is redrawn. To build suspense, we hold two ideas together without resolving them yet, because they are separate cracks that may meet. General relativity predicts an incomplete past, which hints at missing quantum physics near the boundary. The CMB and near-flat geometry hint at an early mechanism that smooths and correlates the universe, even before we invoke quantum gravity. One crack is about the limits of our equations, the other is about the limits of our explanation. Those hints do not yet tell us what the mechanism is, and we should not pretend they do. They tell us what any successful account must accomplish, and that is already a powerful constraint. It must explain why distant regions share a common temperature and spectrum, despite the finite speed of light in an expanding background. It must explain why curvature is so small today without miraculous tuning, and why that smallness persists across cosmic time. It must do this while remaining consistent with the detailed successes of the hot Big Bang. We also need to correct a common misunderstanding about horizons because the word sounds like a physical barrier. A horizon is not always a wall you could fly toward and touch. It is often a boundary of causal contact, defined by the paths light could have taken through an evolving geometry. In cosmology, horizons can change as the expansion history changes, and a region that is out of contact in one era may have been in contact in another. The CMB itself is a practical horizon, because earlier photons were scattered and could not stream freely, making the universe effectively opaque. But the horizon problem is deeper than visibility, and it survives even if we imagine perfect detectors. It is about whether regions could ever have communicated, even in principle, given the expansion history we assume. The question is not, could we see them? The question is, could they ever talk to each other? So the cliffhanger forms naturally. The standard hot Big Bang describes a hot, dense, early universe with precision, and it does so with equations that match observation again and again. Yet its simplest extrapolation runs into a singular boundary and leaves causal puzzles in its wake, as though the universe is telling us two different stories at once. One story is about a thermal beginning we can model, the other is about an earlier chapter that the simplest model cannot comfortably include. At this point we can say what we know and what we do not, and the contrast is part of the drama. We know general relativity works spectacularly well on large scales and moderate curvatures, predicting everything from gravitational lensing to the expansion of the universe. We know the early universe was hot, dense, and close to thermal equilibrium, and we can compute its nuclear chemistry with remarkable success. We also know that the classical equations predict their own failure when pushed far enough back. Geodesic incompleteness is a mathematical statement of that failure, and it is more subtle than a dramatic spike on a graph. It tells us the notion of a smooth path-directed time parameter may be incomplete, because the manifold cannot be extended along certain physical trajectories. In a sense, the universe is not merely missing an earlier time, our theory is missing the ability to define that earlier time in the first place, at least within classical geometry. And we know the universe's large-scale features look prearranged in a way the simplest story does not explain. Uniformity across the CMB and near-flat geometry are not small details that can be brushed aside as coincidences. They're global facts that demand a global explanation, because they involve the entire observable sky and the overall shape of space. When the whole cosmos shares a property, the cause is unlikely to be local. So we end this chapter at the boundary where physics breaks in two ways, and both breaks feel like invitations. One break is theoretical, where singularities signal missing quantum gravity and warn us that the classical continuum may not be fundamental. The other break is explanatory, where horizons and flatness signal missing early universe dynamics, and suggest that the hot Big Bang was not the first act. Together they frame a single, unsettling possibility. The universe may have a prelude that is both physical and conceptual. In the next chapter, we follow the most famous proposal for that missing dynamics, and we treat it as a hypothesis with measurable consequences. We ask how an early accelerated expansion could rewrite horizons, flatten geometry and seed structure, leaving behind the faint patterns we can still read in the CMB, and we ask what that does to the meaning of before, when the universe may have had a dramatic prelude, one that changes not only what happened, but what happened can even mean. The hot Big Bang explains a young, hot plasma, but it inherits unsettling initial conditions that feel almost like hidden assumptions. When we run the equations backward, we do not simply find heat and density, we find a demand for extraordinary coordination. The cosmic microwave background is almost uniform across the sky, even where ordinary causality says contact was impossible. On a full sky map, the temperature varies by only tens of microkelvin. That's a whisper of difference across a sphere of ancient light. Yet the CMB comes from regions that, in a simple Big Bang picture, were never able to exchange signals. Light has a finite speed, and the universe has a finite age. So how did distant patches agree on a common temperature so precisely? Space is also nearly flat, even though decelerating expansion makes flatness unstable over time. The parameter that measures curvature, often written as OK, is observed to be extremely close to zero. In the Friedmann equations, that closeness is not automatically preserved. If the early universe was even slightly curved, decelerating expansion would amplify that curvature's relative importance. Flatness would be a precarious balance, like a pencil standing on its tip. The fact that it still stands invites a mechanism. Inflation enters as a proposed pivot in the early story, not as a decorative add-on. It suggests a brief epoch when the universe expanded at an accelerating rate, before the familiar hot plasma dominated. In that interval, the scale factor grew nearly exponentially. Visually, this is the moment the cosmic grid seems to loosen and surge outward. Imagine a tiny patch of space, smaller than an atom, suddenly swelling until it can contain galaxies. The expansion is not a blast through space. It is space itself changing its scale. Distances ballooned faster than light could traverse them, and that phrase can sound like a paradox. But the speed limit in relativity constrains motion through space, not the growth of the metric. Two comoving points can separate superluminarly without violating local causality. Acceleration in cosmology is not a force pushing galaxies through space. It is the metric itself stretching, so comoving points separate as the geometry evolves. In general relativity, the expansion rate is governed by energy density and pressure together. That pressure term is the subtle piece most people never meet in everyday physics. In the Friedmann acceleration equation, not only energy density but also pressure gravitates. Positive pressure helps slow expansion, while sufficiently negative pressure can do the opposite. In general relativity, accelerated expansion requires a component with high energy density and negative pressure. The condition is often written as R plus 3p0, which is a compact inequality with enormous consequences. It means the cosmic fluid must be strange. A simple model uses a scalar field, often called the inflaton, filling space almost uniformly. A scalar field is just a value at every point, like a temperature field, but with quantum dynamics and a potential energy landscape. In many models it varies slowly, almost frozen. Its potential energy acts like an effective vacuum energy, with pressure near minus its energy density. That equation of state, PER, makes gravity repulsive in the Friedmann equations, driving rapid expansion. The universe behaves as if it is dominated by a temporary cosmological constant. Historically, the idea arrived as a response to real puzzles, not as an aesthetic flourish. In the late 1970s and early 1980s, cosmologists were wrestling with why the universe looks so special. Inflation was proposed as a dynamical way to make special become natural. Inflation is not claimed as certain truth, but as a mechanism with sharp consequences. It is designed to explain why the observable universe looks smooth, flat, and seeded with specific kinds of perturbations. It also moves the documentary's central question, because it reframes what counts as a beginning. Start with the horizon problem, which is really a problem about causal structure. In ordinary radiation and matter domination, the co-moving Hubble radius grows with time. In plain terms, the horizon expands, but it expands too slowly. The co-moving Hubble radius, roughly, AH1, tells us which scales can communicate. When it grows, more regions enter causal contact as the universe ages. But at recombination, the surface that emitted the CMB was divided into many disconnected patches. On screen, you can picture a sphere tiled into thousands of islands of light. Each island has its own past-like cone, its own causal history. The startling fact is that the islands match in temperature as if they once shared the same furnace. Inflation flips that behaviour. During accelerated expansion, the co-moving Hubble radius shrinks, even while physical distances explode. That reversal is the mathematical heart of the horizon solution, and it is easy to miss if you only think in everyday distances. A tiny region that was once causally connected can be stretched to encompass everything we now observe. The patch begins small enough that particles and radiation can interact and equilibrate. Then, inflation magnifies that patch until it becomes the entire visible cosmos. In this picture, the CMB's uniform temperature is not a coincidence across disconnected patches. It is the fossil of a time when those patches were neighbours and could equilibrate. Inflation does not let signals outrun light, but it changes which regions were once within light's reach. Now turn to the flatness problem, which is about curvature's fate in the Friedmann dynamics. Spatial curvature scales differently than matter and radiation as the universe expands. Curvature behaves like a term that falls off more slowly than radiation in a decelerating universe. In a decelerating universe, any small deviation from flatness grows into a large one. That means early conditions must be tuned to astonishing precision if we want near flatness today. The required tuning becomes more severe the earlier you start the clock. Inflation drives curvature towards zero as expansion accelerates. The curvature term is diluted so strongly that space becomes observationally close to Euclidean. Flatness becomes an attractor during inflation, rather than a knife-edge tuning at the start. Visually, curvature is like a wrinkle on a balloon. Inflate the balloon a little, and the wrinkle remains visible. Inflate it by an absurd factor, and the surface looks locally flat everywhere you can measure. This is the dramatic trade inflation offers. It replaces improbable initial uniformity and fine-tuned flatness with a dynamical process that makes them generic outcomes. But it also demands a new ingredient, a high-energy state that behaves unlike ordinary matter. That ingredient is often described as a false vacuum or a field perched on a potential plateau. The field changes slowly, so its energy density stays nearly constant while space expands. The universe becomes dominated by that quasi-constant energy, and the expansion accelerates. The phrase false vacuum carries a useful image for the eye. It suggests a landscape with valleys and ledges where a field can linger in a metastable state. The universe, in this view, is not rolling freely. It is temporarily suspended. Inflation must also end, or it would erase the hot Big Bang we actually observe. Ending inflation requires the field to roll down its potential, and convert its energy into particles and radiation. This reheating repopulates the universe, setting the initial conditions for the hot plasma. Reheating is not a gentle warming. It is a violent conversion of coherent field energy into a bath of quanta, often through oscillations and decays. The details are model dependent, but the narrative role is clear. It restores the universe's familiar thermal story. So the Big Bang becomes, in this framing, not the start of everything. It becomes a transition, the moment inflation ends locally and a hot, dense phase begins. The familiar thermal history starts after reheating, not at the onset of inflation. This shift changes how we imagine the first light. Before recombination, the universe is opaque, a fog of charged particles scattering photons. Before reheating, the universe is not even that fog. It is a different regime, dominated by field energy and geometry. This is where the CMB becomes more than a relic of recombination. Its tiny anisotropies become a test of what happened far earlier, when inflation supposedly operated. The pattern is not arbitrary noise, but a statistical fingerprint of the mechanism that seeded structure. On a CMB map, the mottled blues and reds look almost like weather, but they are not weather in air. They are density and gravitational potential variations imprinted on a radiation field that has crossed the universe for 13.8 billion years. Inflation's most famous claim is that quantum fluctuations were stretched to cosmic scales. Quantum fields cannot be perfectly still, even in their lowest energy states. Their fluctuations are not optional. They are built into the uncertainty principle. During inflation, those microscopic fluctuations are pulled outside the horizon, freezing into classical-looking perturbations. Freezing here means that once a mode's wavelength exceeds the horizon scale, its amplitude stops evolving rapidly. It becomes a persistent imprint on curvature. The key is not that quantum uncertainty becomes large in amplitude. The key is that inflation converts tiny fluctuations into long wavelength variations in density and curvature. Later, when the horizon grows again, those modes re-enter and guide acoustic oscillations and structure formation. You can picture this as a sequence of ripples being laid down on an expanding fabric. Each ripple is born quantum small, then stretched until it spans astronomical distances. Much later, gravity and pressure turn those ripples into the scaffolding of galaxies. These perturbations are predicted to be nearly scale invariant. That means the fluctuation power changes only slowly with wavelength, rather than picking a preferred scale. It's a remarkable property, because many ordinary processes imprint a characteristic size. The CMB's measured spectrum is close to this, which is one reason inflation became dominant. The angular power spectrum shows a broad plateau at large scales, and a series of acoustic peaks at smaller scales. Those peaks are the ringing of the primordial plasma, driven by the initial conditions. In the simplest slow-roll models, the spectrum is not perfectly scale invariant. It has a slight tilt, quantified by the scalar spectral index NNS. The tilt reflects how the inflatant's potential changes with field value, because that change affects the expansion rate and fluctuation amplitude. Observations find NES is a bit less than 1, consistent with many inflationary potentials. That bit less is small, but it is information-rich. It tells us the spectrum is slightly red, meaning more power on larger scales than on smaller ones. Inflation also predicts the perturbation should be mostly adiabatic. Different components fluctuate together, implying a common origin in a single underlying field. In plain language, the universe is perturbed by shifting the overall density, not by swapping one ingredient for another. The CMB strongly supports adiabatic initial conditions, tightening the fit to inflation-like mechanisms. It also constrains isocurvature contributions, which would show up as different peak structures and phase shifts. The data prefer a single dominant source for the primordial pattern. Another prediction concerns Gaussianity. Many inflation models produce fluctuations that are close to Gaussian random fields, meaning the statistics are largely captured by the two-point correlation function. Non-Gaussianity would appear as subtle, higher-order patterns, triangles and quadrilaterals in Fourier space. The CMB is remarkably consistent with Gaussianity, while still allowing small non-Gaussian signals that could discriminate among models. This matters because different inflationary dynamics, such as non-standard kinetic terms, can amplify non-Gaussianity. The sky, in effect, becomes a laboratory for early universe microphysics. but inflation's boldest potential signature is gravitational waves from the early universe. Quantum fluctuations of the metric itself should generate tensor modes, ripples in space-time rather than ripples in density. If detected, they would be direct evidence that gravity was quantized in the early universe. Those tensor modes would leave a distinct imprint in CMB polarization. Polarization is created when photons scatter off electrons in a quadrupole radiation pattern. The early universe, at last scattering, provides exactly the conditions for that imprint to form. Polarization can be decomposed into E modes and B modes. Density perturbations generate E modes efficiently, and those are already measured with high precision. Primordial gravitational waves would generate a specific B mode pattern on large angular scales, a curling signature that density alone cannot easily mimic. The strength of tensor modes relative to scalar modes is summarized by the tensor to scalar ratio R. Many simple inflation models predict ER within reach of experiments, while others predict values far smaller. Measuring R would directly probe the energy scale of inflation, because larger R implies a higher inflationary energy density. This is where the story becomes technically hard and narratively tense. B modes are faint and the sky's full of contaminants. Galactic dust and synchrotron emission produce polarized foregrounds that can mimic the signal, especially when you observe at only one frequency band. Foregrounds are not just an inconvenience, they are a complex astrophysical tapestry, with dust grains aligned by magnetic fields and electrons spiraling in galactic magnetism. To separate them, experiments map the sky at multiple frequencies, exploiting how each source brightens or dims with wavelength. Even if foregrounds are cleaned, gravitational lensing converts some E modes into B modes. That lensing B mode is a real cosmological signal, produced as large-scale structure bends photon paths, but it is a noise source for primordial waves because it adds B mode power where we hope to see the inflationary pattern. Delensing can reduce it, but only with exquisite maps and careful statistics. You need high-resolution measurements of the lensing potential, often using the CMB itself and galaxy surveys together. The challenge is not only sensitivity, but control of systematics that can masquerade as polarization, so inflation is tested in a layered way. The scalar tiltneas is measured and already constrains broad classes of models. Limits on R are improving, but a detection remains elusive, and the absence of B modes does not kill inflation. This ambiguity matters because inflation is not one theory. It is a framework with many possible potentials and field contents. Different models can fit the same scalar data while predicting very different tensor signals, and that flexibility is both a strength and a vulnerability. Inflation also raises a deeper conceptual tension about beginnings. If inflation is driven by a high-energy field, we must ask why that field was there at all. We must ask what prepared the inflating patch, and whether inflation can start without special initial conditions. Some models suggest inflation is a generic attractor, once conditions are roughly right. In those pictures, expansion damps away inhomogeneities and gradients, allowing the field to settle into slow roll. Other models require a rare patch with low gradients and the right field value, a kind of precondition. The horizon and flatness problems may be eased, but the question of initial conditions may simply be relocated. Instead of tuning the hot Big Bang, you tune the onset of inflation. The puzzle changes shape, and we have to decide whether that is progress. Then comes the possibility of eternal inflation. In many potentials, quantum fluctuations can keep parts of the field high on the potential, even while other regions roll down. Inflation ends in some places and continues in others, producing an ever-growing inflating background. In that scenario, reheating happens in bubbles or patches, each becoming a hot Big Bang region like ours. The Big Bang is no longer a global beginning, but a local event inside a larger inflating space-time. Our observable universe becomes one pocket among many, separated by inflating space that keeps stretching. The visuals here almost demand a change of scale. A single bubble universe blossoms like a bright ember in a dark, expanding medium, while new embers ignite elsewhere. The overall picture is not a single explosion, but a perpetually branching process. This is where the word nothing becomes more slippery, not less. If inflation is eternal to the future, it can also be past incomplete depending on the space-time structure. Some theorems suggest inflating spacetimes cannot be extended indefinitely into the past, even if they expand forever forward. So even an eternal multiverse may still require a boundary, a beginning, or a new description. Inflation can push the origin question back, but it may not erase it. It can replace a singular hot beginning with a different kind of edge, where classical space-time stops being a reliable language. The documentary's ladder of nothing now gains a new rung. The pre-inflationary question is not about empty space, because inflation is not emptiness. It is a high-energy state with fields, fluctuations, and a dynamical geometry, and it carries physical content you can, in principle, model. If our Big Bang was a reheating event, then asking what existed before it means asking what existed before reheating. That could be an inflating space-time, not a void. The phrase "nothing before the Big Bang" becomes at minimum misleading because it smuggles in an image of blankness. Yet the deeper question remains: what set the inflaton's potential, and why did a patch begin inflating? What selects the laws and parameters that make inflation possible? And what does selection even mean in a multiverse, where outcomes may be distributed across countless regions? Inflation also forces us to confront time itself. During inflation, the expansion can make regions effectively causally isolated, each with its own local arrow of time. If inflation is eternal, global time ordering becomes subtle, and the idea of a single cosmic clock breaks down. This is not a retreat into philosophy, but a consequence of the geometry. In general relativity, time is part of the metric, and different foliations can slice space-time differently. A multiverse picture can make the word before dependent on how you define time, which is unsettling in a story about origins. So inflation is both a solution and a provocation. It explains why the universe looks smooth and flat, and why primordial fluctuations have their measured spectrum. It also opens the door to a larger cosmos where our beginning is not the beginning, and where initial becomes a local word. We should hold the balance carefully. Inflation is strongly motivated by the horizon and flatness puzzles, and it matches key statistical features of the CMB. But its microphysical origin is unknown, and its model space is broad enough to be hard to falsify with a single measurement. That is why the search for decisive signatures matters. A clean detection of primordial B-modes would narrow the field dramatically, because it would tie inflation to a specific energy scale and a specific class of potentials. A tighter upper bound on R would rule out large classes of simple potentials, forcing more intricate early universe physics. Even without tensors, inflation makes other testable predictions. It links NRNS, R, and possible running of the spectral index to the shape of the potential. It constrains non-Gaussianity, isocurvature modes, and reheating histories that affect late observables, because the expansion history sets how modes map onto today's sky. But the core narrative beat is simpler. Inflation is the moment the universe learned to stretch in a new way, and that stretching rewrote what the sky could remember. It took a small, connected patch and made it the stage for everything we can see. Then it left behind a pattern delicate enough to challenge our instruments. Now we return to the central question with sharper tools. If inflation preceded the hot Big Bang, then the Big Bang was not creation from nothing. It was a change of state, from vacuum-like expansion to a hot particle-filled universe, with entropy and radiation restored. If inflation is eternal in some directions, then our beginning is local and contingent. The word nothing cannot mean the absence of everything, because the larger structure is still something. The mystery shifts to why there is an inflating arena at all, and why its laws permit pockets like ours. And if inflation itself is past incomplete, then even the multiverse may not escape an origin problem. The question becomes what replaces the boundary where classical spacetime fails. That is where quantum gravity and emergent time return to the front, not as speculation, but as the next required step. This is where the CMB's faint ripples become a bridge. They connect laboratory-tested quantum principles to the larger structures in the universe. They also connect the word nothing to a concrete set of physical claims that can be tested, refined, or rejected by data. Next, we ask what it would mean for spacetime to emerge, rather than simply expand. We follow inflation's clues toward quantum cosmology, where beginnings are described by amplitudes, not by earlier moments. The meaning of before will be forced to change again. Before the first heartbeat of time, we imagine a blank stage waiting in darkness, a silent theatre before the curtain lifts. The mind wants a clean emptiness, a pure zero. because it feels simple and complete. But modern physics keeps refusing that image, because emptiness is never simply empty. After inflation, the central question sharpens into a technical demand, and the language stops being poetic. What do physicists mean by nothing when the vacuum itself has structure? What counts as absence in a theory where the basic objects are not things but rules? Quantum field theory starts with a reversal of intuition, and it does so with almost ruthless consistency. Particles are not the basic ingredients, because fields are. In this view, the universe is not built from tiny billiard balls moving through a void. It is built from continuous entities that can vibrate, ripple, and store energy. Every point in space is permeated by quantum fields, even when no particles are present, even when detectors register silence. The vacuum is the lowest energy state of those fields, not the absence of existence. It is a particular condition of a system, like the calmest possible sea that still contains water. To picture it, imagine a dark, translucent grid stretching across the screen, a lattice of possibility rather than matter. Nothing is there in the everyday sense, and yet the grid can tremble. A particle in this language is a localized excitation, an identifiable packet of field energy that behaves like a discrete object. This distinction matters because philosophical nothingness is a stronger claim, and it is almost brutally absolute. It means no objects, no properties, no laws, and no arena in which laws could act. It is not a quiet room, because a room is already something. It is not empty space, because space is already a stage. A quantum vacuum is already an arena with rules, and those rules are not optional. It presupposes fields, symmetries, and a background notion of space-time on which the fields are defined. Even the word state implies a framework that can distinguish one condition from another. So when cosmologists say the universe could come from nothing, they often mean from a vacuum state, and that is a crucial translation. That is a rung on the ladder, not the bottom. The phrase can sound like a metaphysical claim, but it usually points to a specific technical starting point. In quantum theory, the vacuum is not perfectly still, and the reason is not mystical. The uncertainty principle forbids a field and its conjugate momentum from both being exactly zero. The field cannot be pinned to a single value everywhere, while also having perfectly defined motion, because the mathematics disallows that precision. Even at absolute zero, the lowest state retains 0-point energy, and the name is literal. The field still fluctuates around its minimum because perfect rest would require forbidden exactness. The vacuum is the ground floor, but it is not a frozen floor. A useful analogy is a harmonic oscillator, but the point is not metaphorical or merely educational. Each field mode behaves like an oscillator, whose ground state has non-zero energy. In practice, a field can be decomposed into modes, like notes on an instrument, and each note carries a minimum hum. Those ground state fluctuations are not optional noise that we could remove with better instruments. They are the baseline activity of quantum fields, present even when detectors see no particles. What we call empty is a condition with irreducible jitter, a kind of microscopic restlessness. This is where language becomes slippery, because we reach for the phrase virtual particles to make the invisible feel familiar. It can be helpful, but it can also mislead. The phrase suggests tiny objects flickering in and out of being, like fireflies in a dark field. In perturbation theory, internal lines in Feynman diagrams are called virtual, and the term has a specific role. They are bookkeeping devices in an expansion, not literal particles popping in and out. They represent contributions to an interaction amplitude, and they do not obey the same on-shell energy, momentum relation as real particles. Still, vacuum fluctuations have physical consequences that cannot be waved away as mere math, because the predictions land in laboratories. The vacuum can polarize, shift energy levels, and alter forces. It can behave like a medium that responds, even though it contains no material substance. So we ground the abstraction in measurements, because the documentary's mystery must stay accountable to evidence. If the vacuum is restless, it should leave fingerprints. Those fingerprints should show up not as metaphors, but as numbers on instruments. The Casimir effect is one of the cleanest, and it has a beautifully visual logic. Two conducting plates placed close together experience an attractive force, because boundary conditions change the allowed field modes. Between the plates, only certain wavelengths fit, like standing waves on a string that is fixed at both ends. On screen, the plates look like two dark mirrors facing each other, separated by a gap thinner than a hair. Outside, the field can support a richer spectrum of modes, a denser choir of fluctuations. Inside, many modes are excluded, and the imbalance produces a net pressure. The force is not magic pressure from nothingness, and it is not a trick of language. It is a difference in vacuum energy between configurations, measured as a real mechanical effect. In careful experiments, tiny deflections and torsion balances register that pull, turning an abstract subtraction into a physical motion. Historically, this was not an idle curiosity, because it touched the foundations of quantum electrodynamics. Hendrik Casimir proposed the effect in 1948, and it later became a testing ground for how seriously we should take vacuum energy. The details are subtle because real materials are not perfect conductors, and temperature adds corrections. Yet the core lesson survives those complications, and it is hard to unsee once you grasp it. The vacuum responds to boundaries, and boundaries are ordinary objects. Empty space, when constrained, produces measurable forces, and that is a startling kind of intimacy between nothing and something. The Lamb shift is another anchor, and it is older than many people realize. Hydrogen's energy levels are shifted by interactions with vacuum fluctuations and vacuum polarization. The shift is small, but it is not optional, and it appears as a splitting where older theory predicted a degeneracy. In the 1940s, when Willis Lamb measured the effect, it became a crisis and then a triumph. Dirac's early relativistic theory of the electron had predicted certain levels should match exactly, and the atom disagreed. The vacuum, through quantum electrodynamics, supplied the missing correction. Quantum electrodynamics predicts that shift with extraordinary accuracy, and the numbers are almost unsettling in their precision. The vacuum is not a passive void, because it participates in atomic structure. It slightly alters the electron's interaction with the electromagnetic field, and the atom's spectrum records the change. These effects do not prove that empty space is filled with tiny particles like dust in a sunbeam. They show that the ground state of fields has measurable structure and measurable influence. The vacuum is a state with properties, and properties are already a kind of presence. Now we connect this to cosmology, because inflation already hinted that quantum fluctuations seed the sky. The same restless vacuum that shifts atoms can imprint galaxies. The scale changes, but the logic remains, and that continuity is one of the most haunting features of modern cosmology. During inflation, quantum fluctuations of fields are stretched to astronomical scales, and the stretching is violent in its implications. Small quantum variations become classical-looking curvature perturbations after horizon exit. A fluctuation that began as a microscopic uncertainty becomes a pattern written across the observable universe. To visualize it, imagine a smooth, glowing surface that suddenly expands faster than light can cross it, pulling tiny ripples into long frozen waves. Those waves become a faint temperature pattern in the cosmic microwave background, a mottled sky of slightly warmer and cooler spots. Later, gravity amplifies those differences, guiding gas into filaments and halos. That claim depends on the vacuum state chosen for the fluctuations, and the choice is not trivial. Even the phrase, the vacuum, hides assumptions about initial conditions and the geometry. In many calculations, one selects a particular state because it behaves like empty space at very short distances, but that is a physical assumption. In curved space-time, vacuum is not unique, and the reason is technical rather than rhetorical. Different observers can disagree about what counts as particles, because particle concepts depend on time slicing. A particle is defined relative to a notion of positive frequency, and positive frequency depends on how you define time. This is not a philosophical loophole, but a fact embedded in the mathematics of quantum fields. The Unruh effect and Hawking radiation show that horizons and acceleration change particle perception. An accelerating observer can detect a thermal bath where an inertial observer insists there is vacuum, and a black hole horizon turns vacuum fluctuations into radiation for distant observers. So the vacuum is not a single, universal emptiness, like a cosmic default setting. It is a state defined relative to a framework, and the framework includes space-time structure. The emptiness you describe depends on the questions you're able to ask, and on the clocks you use to ask them. That brings us back to Chapter 4's warning about the edge of time, where familiar categories begin to fail. If space-time itself becomes quantum and fluctuating, the idea of a vacuum must be rebuilt. A vacuum of fields on space-time is one concept, and a vacuum of space-time itself may be something else entirely. For now, we stay within the regime where quantum fields live on a classical background, because that is where our tools are sharpest. In that regime, vacuum energy behaves like a kind of energy density. It is not energy you can scoop into a container, but it is energy that appears in the equations. General relativity does not ignore that energy, and it cannot, because gravity responds to stress energy. Any energy density gravitates, and a uniform vacuum energy has a distinctive gravitational signature. It does not clump like matter, and it does not dilute as space expands. A constant vacuum energy corresponds to negative pressure, with an equation of state near P equals minus RO. In the Friedmann equations, that drives accelerated expansion. In plain terms, the vacuum's energy density stays roughly constant while the universe grows, so the total vacuum energy increases with volume. That sounds familiar because we see acceleration today, and the evidence is layered and cross-checked. Observations of distant supernova, plus the CMB and large-scale structure, imply a small positive cosmological constant. The supernovae appear dimmer than expected in a decelerating universe, as if expansion has been speeding up. We call the agent dark energy, but the simplest fit is a constant vacuum-like term. It is gentle, persistent, and it dominates only after the universe becomes dilute. Matter thins as space expands, radiation thins even faster, and the vacuum term eventually wins by refusing to fade. Here the story turns unsettling, because quantum field theory predicts vacuum energy too, and it predicts it in a way that seems unavoidable. If we naively sum zero-point energies of modes, the result is enormous. Every mode contributes its half quantum of energy, and there are infinitely many modes unless you impose a cutoff. In practice, physicists renormalize, subtracting infinities to obtain finite predictions for measurable quantities. That procedure works spectacularly in particle physics, where only energy differences matter. But gravity cares about the absolute level, and that is where the trouble begins, because the subtraction is no longer obviously harmless. The observed cosmological constant is tiny in particle physics units, and the mismatch is not a small discrepancy. It is many orders of magnitude, so many that it feels like a signpost rather than an error bar. The universe accelerates, but it accelerates far less than the simplest quantum estimate would suggest. This is the cosmological constant problem, and it is one of the deepest unsolved puzzles in fundamental physics. It suggests our understanding of vacuum energy is incomplete. It also suggests that the vacuum, which looked like a humble ground state, is entangled with the deepest structure of theory. Some cancellations might occur through symmetry, renormalization, or unknown high-energy physics, and each possibility has been explored with seriousness. Supersymmetry, if exact, would cancel bosonic and fermionic zero-point contributions, but it is broken at accessible energies. Other ideas invoke phase transitions, vacuum selection, or new principles that limit what gravity sees. Yet no explanation is universally accepted, and the problem survives every rephrasing, because the numbers remain stubborn. So the vacuum is powerful enough to accelerate the universe, yet mysterious enough to defy calculation. The same nothing that seems simple becomes a precision crisis. Now we pivot toward origin stories, because the temptation is obvious. If vacuum energy can drive expansion, could a universe begin as a vacuum fluctuation? Could the first chapter of everything resemble the ground state jitter we already know, scaled up to cosmic consequence? Some proposals in quantum cosmology describe creation as a tunneling event, borrowing a concept from ordinary quantum mechanics. A small closed universe could nucleate from a quantum process, then inflate and reheat. The images of a barrier and a crossing, where classical motion is forbidden but quantum amplitude leaks through. In that framing, from nothing often means from no classical spacetime, described by a wave function and boundary conditions. But even then, laws and amplitudes remain. A wave function is not emptiness, and boundary conditions are not silence, because they encode structure. Other scenarios start with a pre-existing vacuum state in a larger spacetime, and the vacuum is not necessarily stable. A metastable false vacuum decays, producing a bubble that becomes a hot Big Bang region. The decay is like a phase transition, where the field rolls or tunnels to a lower energy configuration. That picture resembles eternal inflation's patchwork, with pockets forming in a broader inflating background. Our universe is a local transition, not the global start of everything. The word beginning shifts meaning here, because a beginning for one region may be an event inside a larger story. But each scenario carries hidden structure, and the hidden structure is the point of the chapter. a vacuum requires fields, a Hamiltonian, and a notion of time evolution, even if time is emergent in the final description. You need a space of possibilities and a rule for how possibilities change. A tunneling description requires a configuration space, and a rule for assigning probabilities, or at least amplitudes. A bubble nucleation picture requires a parent spacetime and a vacuum landscape. Even the phrase metastable assumes a potential, and a potential assumes a field with dynamics. So we must be precise about what is being claimed, because precision is the difference between physics and slogan. None of these stories begins from philosophical nothingness, because the machinery of the story is already something. The equations are not passive descriptions because they determine what can happen. This is where the North Pole analogy returns with teeth, and it is more than a clever line. If time is part of the geometry, asking what happened before may be like asking for a coordinate beyond the map. The question presumes a direction that the geometry does not supply. Quantum cosmology sometimes replaces before with boundary condition, and that replacement changes the grammar of origin. Instead of earlier moments, you specify a state or a constraint that defines the whole history. The universe is treated less like a film that starts playing, and more like a complete object with edges defined in a mathematical sense. That move can feel like evasion, because it denies the instinctive demand for a prior cause, but it's also a lesson from physics, learned repeatedly at conceptual cliffs. When the classical road ends, the right question may change form, and the old question may stop being well posed. Still, we can ask what the vacuum contributes to the earliest conditions we can model, and the answer is substantial. Inflation needs a vacuum-like energy to drive accelerated expansion. The inflaton field, if it exists, behaves like a temporary cosmological constant while it slowly evolves. Reheating converts that energy into particles, and the vacuum state determines the spectrum of primordial fluctuations. The vacuum is not an afterthought, because it sets initial seeds. The statistical pattern of those seeds, nearly scale invariant, slightly tilted and close to Gaussian, carries information about the underlying dynamics. Yet inflation also depends on a spacetime background that can expand, and that background is not free. Even if the inflaton is a field, the field lives on geometry, and geometry is not nothing. The expansion rate, the horizon size, and the causal structure are all geometric facts that shape what fluctuations can become. At the Planck scale, geometry itself should fluctuate, and our classical picture becomes a guess with a warning label. Then the distinction between vacuum fluctuations of fields and fluctuations of spacetime becomes blurred. The arena and the actors begin to merge, and the separation we rely on may be only approximate. We do not have a complete theory there, and we should not pretend we do because honesty is part of the drama. But the direction is clear, because the vacuum is already a halfway house. It is nothing only compared to a world full of particles, not compared to the radical absence of structure. It is not nothing compared to the absence of space-time, laws, and the very concept of a state. So Chapter 6 tightens the ladder of meanings step by step. Empty space is not empty, the quantum vacuum is not blank, and even vacuum-based origin stories assume deep scaffolding. Now the narrative rewinds with a new tension that is harder to dismiss. If the vacuum is restless and law-governed, then the origin question becomes about the source of those laws. Why these fields? Why these symmetries? And why this framework in which a vacuum can be defined? We end with a controlled mystery rather than a slogan, because slogans collapse distinctions that physics works to preserve. The quantum vacuum can mimic creation, seed structure, and push space to accelerate, yet it is not the final nothing. It is a richly defined ground state humming with constraints and possibilities. Next, we ask what it would mean for spacetime itself to be emergent, rather than assumed as a backdrop. We follow quantum cosmology toward proposals where the arena is not assumed but produced, and we keep asking carefully what nothing is allowed to mean when the equations refuse to go silent. Before the first heartbeat of time, the word before becomes a trap in grammar, because grammar expects a timeline to stand on. We ask for an earlier moment, yet the theory may deny moments, or deny the very coordinate that makes earlier meaningful. The central question returns with sharper edges, because it sounds simple and yet it targets the foundations. What do physicists mean by nothing before the Big Bang, if time itself is part of what began? General relativity already warned us that time is not an external river flowing past the universe. It is woven into space-time, shaped by matter and energy, and measured by physical processes rather than metaphysical intuition. In Newton's picture, time ticks the same everywhere, even in empty space, even if nothing happens. In Einstein's picture, time is a coordinate that depends on geometry, and geometry responds to what the universe contains. Space and time fuse into a single structure, and the split is observer-dependent, not absolute. Events have positions in space-time, not separate addresses in space and time, and those positions are linked by light cones that define what can influence what. The fusion is not philosophical decoration, because it changes what questions are allowed in the first place. If time is a dimension of the universe, it can have edges, in the same way a map can end without there being more map beyond it. We learned earlier that the Big Bang is not an explosion into pre-existing emptiness, like fireworks in a dark sky. It is the hot, dense early state of an expanding geometry, and the expansion is the stretching of distances within space-time itself. In visuals, imagine a grid drawn on rubber, then pulled wider. Galaxies ride the grid rather than flying through a pre-made void. Run the equations backward and the scale factor shrinks towards zero, while densities and temperatures rise beyond ordinary comprehension. The classical description ends in geodesic incompleteness, not a point you can stand on like a marker in space. A geodesic is the closest thing relativity has to an unforced trajectory, and incompleteness means some world lines cannot be extended indefinitely into the past. In the math, the story stops not because we are bored, but because the model stops giving a well-defined continuation. So the first tension is structural, and it is built into the way time is defined in the theory. Asking what happened before the Big Bang may resemble asking what lies north of the North Pole, and the resemblance is more than poetic. At the North Pole, latitude reaches its limit, and the coordinate system runs out, even though the surface itself remains smooth. North is not hidden beyond the pole, because north is defined by latitude, and latitude has reached its maximum. Cosmological time can behave similarly in standard models, where the Big Bang functions as a boundary of the time coordinate. If the Big Bang is a boundary of time, before is not a location on the map, and the map is the universe. Yet the analogy is not a proof, and it must be handled carefully, because coordinates can fail even when a deeper extension exists. A black hole horizon once looked like a singular edge, until better coordinates revealed smooth space-time across it. The lesson is that some endings are artifacts of description, and physics demands we separate artifacts from genuine breakdown. But some endings are real in the sense of physics, not merely in the sense of charts. Curvature scalars can diverge, and geodesics can truly stop, even in coordinate-free language that does not care about our labels. In a classical Big Bang singularity, tidal forces implied by the curvature become unbounded, and the equations signal that the approximation has been pushed beyond its jurisdiction. The documentary slows here, because the difference between a coordinate edge and a physical edge is the difference between confusion and discovery. This is where the documentary slows into meditation, without leaving physics behind. We need to define time, not assume it, because the universe is not obligated to match our everyday metaphors. In relativity, time is what clocks measure along world lines, and a clock is any physical process with a regular, countable rhythm. Proper time is local, and different paths through space-time accumulate different durations, even if they begin and end at the same events. That is time dilation in its cleanest form, and it is not a trick of perception. Motion and gravity change the rate of clocks, because geometry changes the metric along the path, and the metric is what converts coordinates into physical intervals. A fast-moving particle in an accelerator literally experiences less proper time between two lab events than the lab does. A clock deeper in a gravitational well ticks more slowly than one higher up, and GPS satellites must correct for this or navigation would drift. So there is no single universal time that all observers share, not even in principle. There is a web of local times stitched together only under special conditions, and those conditions are cosmological assumptions rather than logical necessities. Cosmology uses one of those special conditions because on large scales the universe is close to homogeneous and isotropic. That near uniformity is an empirical fact, inferred from galaxy surveys and the astonishing smoothness of the cosmic microwave background. Because of that symmetry, we can define cosmic time. a shared parameter that tracks the expansion. Cosmic time is the time measured by co-moving observers who ride the expansion, meaning observers who see the universe as statistically the same in every direction. In an FLRW universe, that shared clock is mathematically natural, and it labels slices of constant density and constant temperature in the idealized model. In visuals, picture a loaf of raisin bread rising, with each raisin at rest in the dough while distances between raisins grow. This is the time used in the familiar timeline, the one that fits on museum walls and classroom posters, recombination at about 380,000 years, when electrons and protons formed neutral atoms and light finally travelled freely. Nucleosynthesis in the first minutes, when the first helium and deuterium were forged in a nuclear furnace. Inflation earlier still, if it occurred, stretching quantum fluctuations into the seeds of cosmic structure. But cosmic time is not guaranteed near the beginning, and the closer we push toward the earliest instance, the more conditional the clock becomes. As we approach extreme energies, quantum fluctuations and anisotropies can spoil the clean slicing, and the idea of a single smooth foliation may lose physical meaning. Even classically, strong inhomogeneity can break the notion of a global clock, because different regions evolve differently, and no single preferred time coordinate remains. The universe can be globally complicated even if it looks locally simple, and the early universe may have been both. Inflation was introduced as a mechanism that smooths and flattens, and historically it was motivated by puzzles in the standard Big Bang picture. The horizon problem asked why distant regions share nearly the same temperature, even though they seem too far apart to have exchanged signals. The flatness problem asked why the universe's spatial geometry appears so close to Euclidean, requiring delicate tuning without a dynamical explanation. Inflation offered a dramatic fix by rapidly expanding a tiny, causally connected patch into the observable cosmos. It also makes cosmic time feel more meaningful inside an inflating patch, because the expansion tends to erase curvature and dilute irregularities. Yet inflation raised its own origin problem, because it is not merely a mechanism but a regime that must begin. What prepared the inflating region, and what counts as earlier if the background may be past incomplete? Some theorems suggest that even an eternally inflating space-time cannot be extended indefinitely into the past, which pulls the origin question back into view. So we face two clocks at once, and neither is guaranteed to survive the trip to the beginning. Local proper time is always defined along a path, while cosmic time is a global convenience that may fail when symmetry fails. Near the Big Bang boundary, even local time becomes subtle, because the definition presumes a classical world line. If space-time itself becomes quantum, the notion of a classical trajectory may dissolve into a superposition of geometries and histories. That pushes us toward a deeper question, one that sounds philosophical but is forced by the physics. If time is part of the system, what does it mean for the system to evolve, and what does evolution even refer to? In ordinary physics, evolution is change with respect to time, and time is an external parameter in the equations. In quantum cosmology, time may not be an external parameter you can plug into equations, because there is no outside clock for the universe. The origin question shifts from earlier moments to boundary conditions, and that shift changes the emotional shape of the mystery. Instead of asking what happened first, we ask what defines the whole history, including the conditions that make a classical time parameter emerge. This is not a retreat into wordplay, because it is forced by the structure of the fundamental equations when applied to the universe as a whole. When the system is everything, there is nothing external left to serve as the reference frame. Now the arrow of time enters, because time is not only a coordinate on a diagram. Time has a direction in experience, and physics must account for that asymmetry without smuggling it in by assumption. Microscopic laws are mostly time reversal symmetric, meaning they do not care whether a process runs forward or backward. Yet macroscopic processes are not, because entropy tends to increase, and because the universe keeps producing irreversible records. The second law of thermodynamics is statistical, not absolute, and that detail matters. It says that in an isolated system the number of accessible microstates typically grows, because there are vastly more disordered arrangements than ordered ones. Entropy measures the count of possibilities, and it is a measure of information in a precise physical sense. High entropy means many microscopic arrangements look the same macroscopically, while low entropy is special and fragile. The arrow of time is then the arrow of increasing entropy, and it is also the arrow of memory and causation as we live them. We remember the past because records are low-entropy structures created by irreversible processes, like footprints in drying mud or photons scattered into the environment. A record is not magic. It is a physical correlation that cost entropy to create and maintain. The universe's ability to store records depends on its thermodynamic gradient, and that gradient depends on how it began. Cosmology makes this sharper because the universe is the largest isolated system we know, at least to the limits of observation. If entropy increases, it must start low, and that requirement is not optional if we want an arrow at all. That is the profound mystery of the early universe, and it is easy to misunderstand because the early universe was hot. The hot Big Bang was not maximum entropy, even though it was hot and dense and close to thermal equilibrium for ordinary matter. A uniform thermal plasma sounds disordered, because in a lab uniformity can be the end state. But gravity changes the bookkeeping, because gravitational systems have more ways to be clumpy than smooth, and clumping opens an enormous space of configurations. For gravitating systems, clumping can increase entropy dramatically, and the most extreme clumps are black holes. A smooth early universe is gravitationally low entropy, a state with enormous unused phase space, because gravity could have made dense structures, but did not. Black holes carry vast entropy, proportional to horizon area, a result associated with Bekenstein and Hawking. The early universe had almost none of that horizon entropy, despite having the mass energy to form it, and that absence is a quantitative clue. In visuals, the camera could drift over a smooth, nearly featureless CMB map, then dissolve into a field of black holes that never formed. The contrast is the puzzle. The universe began in a state that seems improbably ordered from gravity's perspective. So the arrow of time is not explained by expansion alone, because expansion can occur in many entropy conditions. It is tied to an initial condition that seems extraordinarily special, and specialness is exactly what physics tries to avoid positing without explanation. Inflation is sometimes invoked as a partial explanation, because it can smooth and dilute inhomogeneities in the matter distribution. But inflation itself must start in a suitable state, and that state may already encode the low entropy condition we are trying to explain. If inflation requires a low entropy patch, the puzzle is relocated rather than solved, and relocation is not resolution. If inflation creates low entropy, we must specify what entropy means during inflation, because the relevant degrees of freedom are not the same as in a gas. Either way, the arrow points back to a boundary condition, and the boundary condition is where the universe seems to hide its most consequential secret. The universe appears to begin in a state that makes time's direction possible, and that fact is as empirical as it is conceptual. This connects to the central question about nothing, because nothing is often imagined as a blank stage. If the beginning is a boundary condition, then nothing is not emptiness, but a rule about allowed histories, a constraint on what a universe can be. We can now restate the North Pole analogy with more precision, because the analogy is about coordinates and boundaries, not about geography. The Big Bang may be a boundary of space-time, not an event inside a larger time, and that distinction is the heart of the chapter. In that case, asking what happened before is like asking for a point with latitude greater than 90 degrees, and the coordinate request has no answer. But physics also offers a second option, and it keeps the mystery alive rather than shutting it down. The Big Bang might be a boundary only in classical coordinates, while a deeper description smooths it, the way quantum mechanics smoothed classical catastrophes in earlier revolutions. The singularity could be a sign that we're using the wrong language at the wrong scale. Quantum gravity is where such smoothing could happen, because at Planck scales the classical picture is expected to fail. At those energies, geometry may fluctuate, and the classical singularity may be replaced by something finite, perhaps a transition rather than a beginning. One family of proposals treats the beginning as a boundary rather than a moment, and the phrasing matters. The universe is finite in a time-like direction, yet has no edge, meaning there is no sharp boundary where the laws must specify arbitrary initial data. This is where Hawking's no-boundary idea enters, with the quiet audacity of a mathematical reframe. It proposes that the universe has no initial boundary in the usual sense of time, even if it has a smallest size. The technical move uses imaginary time, where time behaves like another spatial dimension, and the metric signature changes in a controlled way. Near the beginning, the metric becomes Euclidean rather than Lorentzian, which is a precise statement about the geometry, not a claim about human experience. In that picture, the beginning is like the smooth cap of a sphere, and the image is meant to be literal in the mathematics. There is a smallest size but no sharp corner where laws must specify a start, and no singular point where curvature becomes infinite. The North Pole returns again, now as geometry rather than analogy, because a sphere has a pole yet the surface has no boundary. You can walk to the pole, but you cannot walk off the surface, because there is no edge to fall from. Imaginary time is not a claim that time is literally imaginary in experience, and the documentary should not let the metaphor run wild. It is a mathematical continuation used to define a well-behaved path integral, a way of summing over possible geometries without the oscillations that plague the Lorentzian version. The no-boundary proposal aims to replace initial conditions with a regularity condition, and regularity is a constraint with teeth. The universe is selected by requiring smoothness at the cap, which narrows the space of allowed histories. That changes the origin question, because it shifts the burden from a first moment to a global constraint. Instead of a first moment that demands a cause, we have a boundary condition that constrains the whole space-time, including the emergence of classical time. Yet the tension remains because a boundary condition is still something, and something is not nothing. It is a law-like selection rule, and it presupposes a framework of quantum states, amplitudes, and a notion of what counts as a possible geometry. So we ask the harder version of the central question, the version that does not let us hide behind imagery. What does it mean for laws and quantum states to exist without time, and what does existence mean in a timeless formalism? In standard quantum mechanics, states evolve with time under a Hamiltonian, and the Hamiltonian tells the system how to change. In quantum cosmology, the Hamiltonian constraint can erase external time, because general relativity treats time reparameterizations as gauge, not as physical change. The Wheeler-DeWitt-style picture replaces evolution with a static equation, and static here means timeless, not frozen in a moment. The universe is described by a wave function over geometries and fields, a distribution of amplitudes across possible configurations. Then time must emerge as an approximate concept inside certain semi-classical regimes, where one part of the system behaves like a clock. Clocks become internal degrees of freedom correlated with others, and the correlations generate an effective sense of sequence. This is the idea of relational time, and it is both subtle and concrete. Change is described by correlations, like one variable serving as a clock for another, and the clock is not privileged by fiat. It sounds abstract, but it matches the warning we already received, because if space-time is dynamical, time cannot be assumed as a background parameter. The beginning of time could mean the breakdown of the semi-classical approximation, where the universe no longer supports stable classical clock variables. Before that, there may be no classical clock to define before, and the word itself becomes unmoored. This is where cosmic time and local time both fail together, and the failure is not a psychological failure. Without a stable geometry, co-moving observers are not well defined, and world lines are not classical, so proper time becomes a derived approximation too. The documentary's ladder of nothing climbs again, because empty space is not nothing, vacuum is not nothing, and the absence of time is a deeper rung. Now we tighten the narrative stakes because the consequences are not confined to the beginning. If time emerges, then causality becomes emergent too, because causality relies on temporal ordering and light cone structure. That does not mean anything can happen, and it does not grant permission to abandon rigor. It means the fundamental description may be non-temporal, and temporal cause and effect is a derived story that becomes accurate only when time becomes a good approximation. This is difficult because our intuitions are built from time, and they resist being demoted. We ask what caused the universe, but causation is a concept inside time, and it presumes a direction. If the arrow of time itself depends on a boundary condition, then causal language may be downstream of the very thing we're trying to explain. So the origin question transforms rather than disappears, and transformation is the documentary's central move. We stop asking what happened before, and start asking why this history is allowed at all, given the space of possible histories. We also ask what selects the laws, because if the universe is described by a wave function and boundary conditions, why those and not others? Eternal inflation sharpened this selection tension, because it suggests many pocket universes could exist with different effective parameters. If many outcomes occur, selection becomes statistical or anthropic, and the word explanation takes on a different shade. but past incompleteness theorems suggest even inflation may require a boundary, which keeps the beginning in play. A multiverse can be endless forward, yet still have an edge backward, and that edge becomes the new origin question. So time's beginning is not a parochial detail, and it is not merely a curiosity for philosophers. It is the hinge on which every origin story swings, including inflationary ones, because every story needs a rule for what counts as allowed. Now we return to the arrow of time with new force, because the arrow is a measurable constraint. If the beginning is a boundary, the low entropy condition must be encoded there, not appended later as an afterthought. No boundary style proposals sometimes claim to favour smooth, low entropy beginnings, and the claim is part of their appeal. But the details are contested, and the measure problem looms, because probabilities in cosmology depend on how you count histories. Other models propose a bounce where contraction precedes expansion, and the universe avoids a singular beginning by transitioning through a minimum size. In those scenarios, time may extend through the bounce, but the arrow must be explained on both sides, not only on ours. A bounce can trade a beginning for a transition, and transitions can be just as demanding as beginnings. It inherits its own constraints, because entropy and anisotropy can grow during contraction, threatening to overwhelm the smoothness we observe. So the arrow of time remains a diagnostic, and diagnostics are how science keeps metaphors honest. Any viable model must explain why entropy was low in the early expanding phase we infer from data, not merely assert that it was. This is where the documentary's dramatic tone earns its place, because the stakes are physical and observational. The universe is not only expanding, it is remembering, and remembering requires a symmetry, because a perfectly time-symmetric universe would not generate durable records. The CMB is a fossil of early conditions, and it carries the imprint of a remarkably ordered start. Its tiny temperature variations, at the level of tens of microkelvin, encode the primordial fluctuations that later grew into galaxies and clusters. The smoothness we see is part of the entropy puzzle, because smoothness is gravitational order, not gravitational disorder. In visuals, the camera can glide across the mottled CMB sky, then zoom into the web of galaxies that the mottling eventually became. Inflation explains smoothness dynamically, but it still leans on a special state, and the specialness is the recurring refrain. Quantum cosmology can reframe the state as a boundary condition, not a moment, which changes how we talk about beginnings. That reframing changes what nothing can mean, because nothing becomes not a void, but the absence of classical time and classical geometry. Yet even that is not pure emptiness, because a timeless quantum description still contains structure, like a space of states and a rule for amplitudes. So we hold two truths at once, and the tension between them is the chapter's atmosphere. Physics can make before meaningless, and physics can still require a deeper something that replaces time, even if it is not time as we know it. This chapter's core claim is not that time definitely began, and it is not that time definitely did not. It is that the question is technical, and our language must follow the math, even when the math undermines our most basic intuitions. Relativity makes time part of the universe, not a container around it, and that is a historical rupture as well as a scientific one. Thermodynamics makes time directional, and that direction demands a special beginning, a low entropy boundary that sets the gradient. Cosmology offers a shared clock, but only under symmetry assumptions that may fail near the threshold where quantum gravity matters. Quantum proposals replace first moments with boundaries, and boundaries are both elegant and unsettling, because they answer one question by sharpening another. The mystery deepens because the origin question survives every translation, and survival is itself a clue. If time emerges, then the deepest level is not earlier but more fundamental, and fundamental is not a time word. This is where the documentary's hook returns, now stripped down to its hardest form. Before the first heartbeat of time, what could hold reality up, and what could the phrase hold even mean? Next, we test boundary ideas against what the sky actually measures. We ask which proposals leave fingerprints, and which remain only elegant grammar, beautiful but unaccountable. We move toward the climax by demanding accountability, because cosmology is not only a story about origins. A beginning without time must still connect to the universe we observe, or it is only a story. Before the first heartbeat of time, the mind still demands a first scene, because narrative instinct hates an unfinished sentence. General relativity answers with a boundary, where its own equations fail, an edge marked by infinite curvature in the mathematics. This chapter asks whether that boundary is a true beginning or a transition disguised as an ending. The central question returns with sharper stakes, because the word nothing is doing heavy work in cosmology. What do physicists mean by nothing before the Big Bang, if the Big Bang was not first? In the standard picture, before is not just unknown, it is undefined, because time itself is part of what begins. Several competing models replace the singular start with a prior phase, and each rewrites what before can mean. We begin with the simplest reversal of the standard story, which is also the most visually intuitive. Expansion might have been preceded by contraction, with the Big Bang as a bounce, like a spring compressed to its limit. In that picture, the universe did not appear from nothing, and it did not need a first instant. It passed through an extreme state where classical spacetime lost authority, then re-emerged, expanding into the hot, bright plasma we infer from the sky. On screen, the scale factor curve falls like a slow tide, steepens into a plunge, then rounds off instead of diverging. The crucial claim is modest but radical. The curve bottoms out at a finite minimum, not at zero. That minimum is not a comfortable place, because densities approach the Planck scale, where quantum effects should dominate. Yet it is precisely there that a beginning can be replaced by a passage. A bounce is not automatically a solution, because contraction is dangerous in a technical, unforgiving way. In a contracting universe, anisotropy tends to grow and shear can dominate, so the geometry can stretch into a lopsided, jagged collapse. Small inhomogeneities can amplify, and the approach to a crunch can become chaotic, reminiscent of the old BKL picture of mixmaster behavior. Any bounce model must explain why our universe emerged smooth enough to match the CMB, with its near-uniform temperature and its exquisitely regular acoustic peaks. The danger is not merely aesthetic, because the CMB is a quantitative ruler. Its fluctuations are at the level of 1 part in 100,000, and their statistics are close to Gaussian. A contracting phase that generically amplifies anisotropy must be tamed, or it will leave scars too large to hide. So the bounce is not a single event, but a demand for a controlled history on both sides of it. Quantum gravity is the usual tool invoked to prevent the singularity, because classical general relativity drives curvature and density toward divergence. In the Friedmann equations, energy density acts as a source of curvature, and the classical solutions can run to a point where the equations themselves lose meaning. Quantum geometry can modify the Friedmann equations at high density, making gravity effectively repulsive near the Planck regime. That repulsion can halt contraction and trigger expansion not by magic, but by altering how spacetime responds when it is pushed beyond its classical limit. This is where the documentary's visuals can slow down and become tactile. Spacetime is no longer a smooth fabric, but a structure with an underlying grain, an idea that is hard to picture and easy to misunderstand. The claim is not that space is made of tiny cubes in a simple grid. The claim is that geometric quantities, like area and volume, may come in discrete units, so the continuum approximation breaks down when the universe becomes too small. Loop quantum cosmology is a flagship example of this logic, and it has a clear narrative hook. It treats geometry as quantized, with discrete spectra for areas and volumes, derived from the loop quantum gravity framework applied to highly symmetric cosmological settings. At very high density, effective equations include correction terms that cap the energy density, so the classical divergence is replaced by a maximum. The classical singularity is replaced by a minimum scale factor and a deterministic bounce, where the evolution can be extended through what used to be the end of time. In many presentations, the key modification appears as a simple factor in the Friedmann equation, often written so that the Hubble rate goes to zero at a critical density. That critical density is typically near the Planck density, where quantum gravitational effects are expected to matter. The result is a turning point. Contraction slows, stops, and reverses. The mathematics is clean in its idealized form, and that cleanliness is part of its appeal. This is not a free victory over the beginning, because the hard questions simply move to a deeper layer. The model must still specify a quantum state for the pre-bounce universe, and that choice is not automatically dictated by the theory. It must explain how perturbations pass through the bounce without losing the phase coherence seen in acoustic peaks, which act like a cosmic interferometer. It must also recover standard nucleosynthesis and recombination with no hidden damage. because those epochs are fixed by multiple independent observations. The perturbation issue is especially delicate because the CMB peaks are not just bumps in a graph. They encode coherent oscillations in the photon, baryon fluid, frozen into the sky at recombination. If the bounce scrambles phases, adds excessive isocurvature modes, or distorts the transfer functions, the pattern will not match what Planck and other experiments measure. So the bounce must be gentle in a very specific way, even if the energy densities are extreme. The observational question becomes concrete, because cosmology has matured into precision inference rather than philosophical speculation. Does a bounce leave features in the primordial power spectrum, like oscillations or a cut-off at large scales, where the largest modes may have interacted with the bounce most strongly? Does it predict a different tilt or running than slow-roll inflation, changing how power shifts across scales? Does it generate non-Gaussian correlations beyond Planck limits, revealing interactions or multi-field dynamics in the early universe? These are not abstract maybe signatures, because the primordial spectrum is a fossil record. A cutoff at low multipoles could hint that the largest wavelengths never experienced the same smoothing history as smaller ones. Oscillations could be the imprint of matching conditions across a transition, like ripples left after a sudden change in medium. Each feature would be small, but the data are now good enough to make small differences matter. Tensor modes become a decisive pressure point, because they are hard to fake. Many bounce scenarios suppress primordial gravitational waves because the mechanism for scalar perturbations differs from inflationary stretching, and the background evolution can damp tensor production. Some versions can produce tensors, but often with a blue tilt that shifts power to smaller scales, away from the CMB window. Future B-mode searches can turn this into a test, not a preference, because a clean detection would narrow the space of viable histories. On screen, the comparison is stark. One panel shows inflation-like tensors rising gently across CMB scales, while the other shows a suppressed curve hugging the axis. The narrator can linger on the idea that gravitational waves are not just waves in space. They are waves of space-time itself, and they carry information about the expansion history in a way that density perturbations do not. Now we widen from a single bounce to repeated history. Cyclic models propose that expansion and contraction occur again and again, so that the Big Bang becomes a recurring event, not a unique origin. The word nothing is rejected, replaced by an eternal sequence with no first cycle. In this view, the universe is not a story that begins, but a rhythm that repeats, even if the details evolve. Cyclic universes face an old thermodynamic trap that has haunted cosmology since the 19th century. Entropy tends to increase, and each cycle can inherit the disorder of the last, because irreversible processes leave a permanent accounting. If entropy accumulates without a reset, later cycles become longer and larger, and the past cannot be truly periodic. Any cyclic proposal must explain how entropy is diluted, exported, or redefined, without quietly smuggling in a special initial state. The trap is not merely philosophical, because entropy is tied to observable structure. Black holes, for example, store enormous entropy, and their presence would complicate any attempt at a clean reset. Radiation backgrounds, relic particles, and defects can also accumulate, leaving a universe that becomes progressively harder to recycle. So the cyclic promise of eternal recurrence comes with a bookkeeping problem that refuses to go away. Some cyclic models try to use expansion itself as a dilution engine, and the idea is simple enough to visualize. If each cycle includes a phase of accelerated expansion, the observable region can be effectively cleaned, because entropy is spread over a vastly larger volume. But then the model begins to resemble inflation, and it inherits inflation's questions about initial conditions and measure. The cycle becomes a framework that still needs a deeper rule, because dilution is not the same as erasure. Another family of cyclic ideas aims for a different kind of smoothing, and here the dynamics are almost counterintuitive. Ekpyrotic scenarios use a slow, ultra-stiff contraction before the bounce, driven by a field with an equation of state much larger than 1. During this phase, the energy density of the ekpyrotic component grows faster than anisotropy and curvature terms, so it can dominate and suppress them. The universe is smoothed not by rapid expansion, but by a controlled, flattening collapse, like a wrinkled sheet pulled taut as it shrinks. This is a subtle point, and it deserves a few extra seconds of narration. In ordinary contraction with matter or radiation, anisotropy terms can grow disastrously. In ekpyrotic contraction, the dominant component scales so steeply with the scale factor that it overwhelms those dangerous contributions. The result is a kind of attractor behavior toward homogeneity and flatness, achieved in reverse compared to inflation's accelerated expansion. Ekpyrosis changes the origin of primordial structure, which is where the model becomes testable. In many versions, scalar perturbations arise from entropic modes in multiple fields, then convert to curvature perturbations through a bending trajectory in field space. The mechanism can produce a nearly scale-invariant spectrum without standard inflation, and it can preserve the phase coherence needed for the CMB peaks. It often predicts distinctive non-Gaussianity, sometimes of the local type, which data can constrain with increasing precision. The conversion from entropy to curvature is not a decorative detail, because it shapes the statistics of the sky. Multi-field dynamics can generate correlations that single-field slow-roll inflation tends to suppress. That is why the bispectrum, and not just the power spectrum, becomes a battleground. The universe is not only telling us how much structure exists at each scale, but also how that structure is distributed and correlated. The gravitational wave story shifts again, and the shift is almost a signature in itself. Ekpyrotic contraction typically produces negligible primordial tensor modes at CMB scales, because the background evolution does not amplify them the way inflation does. That absence becomes a signature if future experiments detect a robust inflationary-like tensor signal with the expected spectral shape. If tensors remain undetected, ekpyrotic models gain room, but they still must match all scalar statistics, including subtle constraints on running and non-Gaussianity. A bounce also raises the arrow of time question from Chapter 7, and it does so with a new sharpness. If time extends through the bounce, does entropy increase on both sides, or does the arrow reverse at the turning point? Does it point away from the bounce in both directions, making the bounce a kind of temporal watershed? Different answers imply different boundary conditions, and boundary conditions are never nothing. Some proposals treat the bounce as a special low-entropy surface, and that choice is as powerful as it is suspicious. The universe could be most ordered at the bounce, with entropy increasing as it expands in either temporal direction. That makes the bounce a kind of thermodynamic origin, even if it is not a temporal origin, an origin of disorder rather than an origin of time. The model must justify why such a special surface exists, because special is another word for assumed. Other proposals keep a single arrow through the bounce, so that the past and future are not symmetric. Then the pre-bounce phase must be extraordinarily low entropy already, or it must include a mechanism that sheds entropy before the crunch, perhaps by moving it beyond the observable patch. Without that, the contracting universe becomes too messy to produce our smooth CMB, and the bounce becomes a blender rather than a bridge. The entropy problem becomes a filter that eliminates many attractive sketches, even when their equations look elegant. Now we step into higher dimensions, where the Big Bang becomes a collision. Brain-world cosmology imagines our observable universe as a three-dimensional brain embedded in a higher dimensional bulk, an idea that gained traction alongside developments in string theory in the late 1990s and early 2000s. Matter and radiation are confined to the brain, while gravity can explore the extra dimension, which helps explain why gravity appears so weak compared to other forces. The bang is then a brain interaction, not a creation event, and the beginning becomes a moment of contact. Visually, the bulk is a dark volume, and within it a luminous sheet carries galaxies like dust on glass. Another sheet drifts closer, and the distance between them becomes a single, ominous parameter. The collision is not a cartoon punch. It is a transfer of energy that reheats the brain into a hot plasma, setting the initial conditions for the hot Big Bang phase we know. The ekpyrotic picture originally grew from this brain language, and that origin matters for how the story is told. Two brains approach in the extra dimension, collide, and reheat the brain into a hot plasma, with the temperature jump playing the role of the Big Bang. The collision replaces the singularity with a physical process in a larger spacetime, where the bulk provides a stage that predates the event. Nothing is replaced by a prior bulk history, and the word before becomes meaningful again in a literal sense. This move changes what must be explained, and it does so with a kind of ruthless honesty. Why did the brains exist, and why were they moving rather than sitting in a static configuration? What sets the potential that drives their approach, and what stabilizes the extra dimension afterward so that physics does not drift? The model trades a four-dimensional singularity for a higher dimensional initial condition, and the origin question simply climbs one rung up the ladder. Brain collisions also face perturbation constraints, because the CMB is not impressed by imaginative geometry. The collision must generate adiabatic, nearly Gaussian, phase-coherent fluctuations consistent with the CMB peaks, which means the perturbations must be seeded with the right correlations. It must avoid producing excessive isocurvature modes, which are tightly limited by data and would show up as mismatched peak structures. It must also avoid relic defects or anisotropies that would spoil the sky, because the universe we see is remarkably clean. In these models, the phrase "before the Big Bang" becomes literal again, and that literalness is both thrilling and dangerous. There is a time parameter in the bulk, and the collision happens at a finite bulk time, so the story can be extended backward without immediately breaking the grammar of time. Yet the documentary's ladder of nothing still applies, because a bulk space-time is not nothing. It is a larger stage with more structure, more degrees of freedom, and more assumptions hiding in the dark. Across bounce, cyclic, and brain scenarios, the same demands keep returning, like a refrain that refuses to fade. They must reproduce the observed scalar power spectrum, including its near-scale invariance and slight red tilt, which encode the early universe's dynamics with surprising precision. They must preserve Gaussianity to the level Planck observes, while allowing small deviations we can hunt with future surveys. They must explain why perturbations are adiabatic and why phases line up, because coherence is a signature of a specific kind of origin. They must also respect the hot Big Bang successes, which are not optional details in the narrative. Big Bang nucleosynthesis fixes the baryon density and expansion rate minutes after reheating, and it does so through the abundances of light elements like helium and deuterium. Recombination fixes the acoustic physics that shapes the CMB peaks, locking in the sound horizon and the damping scale. Any alternative beginning must connect cleanly to that evidence, not merely gesture at it from a distance. The horizon and flatness problems reappear in new clothing, because they are really questions about why the universe looks so uniform and so close to geometrically flat. Inflation solved them by shrinking the comoving Hubble radius during accelerated expansion, allowing regions now far apart to have once been in causal contact. Bounce and ekpyrotic models must solve them with different dynamics, often by making the comoving Hubble radius shrink during contraction. The mechanism differs, but the observational target is the same, and the target is written across the entire sky. This is where the vacuum from Chapter 6 becomes a hidden constraint, and it is easy to underestimate its reach. Inflation's predictions depend on a choice of vacuum state for fluctuations in curved spacetime, which is not uniquely defined in a time-dependent background. Bounce and cyclic models also require a prescription for initial perturbations in a pre-bounce phase, where the notion of empty is equally subtle. Vacuum non-uniqueness becomes a shared vulnerability, not an inflation-only worry, because the early universe forces quantum field theory into its most delicate regime. The cosmological constant problem also shadows these alternatives, because it is a reminder that our understanding of vacuum energy is incomplete. If vacuum energy gravitates, why is today's acceleration so small compared to naive quantum estimates, which overshoot by absurd orders of magnitude? Some cyclic ideas try to relax the cosmological constant dynamically over cycles, allowing the value to drift towards smallness. Others embed the problem in a landscape of vacua, shifting the question to selection and measure, and the documentary keeps the unease alive. Observational handles become the chapter's spine, because the sky is the referee, and referees do not negotiate with metaphors. Non-Gaussianity is one handle, because different mechanisms generate different shapes and amplitudes in higher point correlation functions. Local non-Gaussianity can point to multi-field conversion processes common in ekpyrotic models, where entropy modes are converted into curvature perturbations. Equilateral and orthogonal shapes can indicate non-trivial dynamics or higher derivative effects, and each shape is a fingerprint rather than a decoration. Tensor modes are another handle, because they trace the expansion history in a way that is hard to counterfeit. A detectable primordial B-mode signal with a near-scale invariant tensor spectrum would strongly favour inflation-like stretching, because it would imply a high energy scale and a specific background behaviour. A stringent upper bound pushes weight toward alternatives that naturally suppress tensors, including many ekpyrotic and some bounce scenarios. Either outcome is information, and the documentary treats it as a narrowing corridor rather than a victory lap. Features in the primordial power spectrum offer a third handle, and they are the kind of evidence that rewards patience. A bounce can imprint oscillations, a cutoff, or a change in slope at the larger scales, where modes may have experienced the transition differently. A cyclic transition can leave localized glitches tied to a specific event in the prehistory, like a brief departure from an attractor phase. These signatures are subtle, but they are the kind of subtlety precision cosmology was built to chase, one multipole at a time. Large-scale anomalies become tempting but dangerous evidence, because humans are pattern-finding machines. Low multipole oddities in the CMB can be statistical flukes, foreground artifacts, or hints of pre-inflationary physics that touched only the largest modes. Bounce models sometimes claim to explain missing large-scale power or unusual alignments, and the claims are not always empty. The documentary keeps the tension without granting a verdict, because the line between anomaly and coincidence is thin. Structure formation and lensing add cross-checks, and they do so with a welcome brutality. The same primordial spectrum that shapes the CMB also shapes galaxy clustering and weak lensing, and those datasets probe different epochs and different systematics. A model that fits the CMB but fails large-scale structure is not a viable replacement, no matter how elegant its origin story sounds. Consistency across datasets becomes the standard, not rhetorical elegance, because the universe is one object observed in many ways. The measure problem lurks behind many cyclic and multiverse-adjacent ideas, and it can quietly undermine predictability. If there are many cycles or many regions, how do we define probabilities for what we observe, rather than what exists somewhere? Different measures can change predictions, and that makes the theory slippery when confronted with data. A model that cannot specify what it predicts cannot be tested, and an untestable model cannot settle the question of beginnings. Bounce models face their own version of this issue, even when they avoid explicit multiverses. If the pre-bounce phase is long, what selects the state that enters the bounce, rather than another state that would lead to a different post-bounce universe? If many histories lead to different post-bounce outcomes, selection returns again, now wearing quantum clothes. The beginning is avoided, but the question of why this history remains, and not another, still presses against the glass. Now the chapter tightens its dramatic claim, because the alternatives are not merely technical variations. These alternatives do not merely compete with inflation, they compete with the idea that the universe had to begin at all, at least in the sense of a first moment. They offer a cosmos where nothing is not the starting point, and where the Big Bang is a chapter break, violent, transformative, but not necessarily the opening page. But each alternative pays a price in deeper assumptions, and the price is not hidden for long. A bounce needs quantum gravity corrections that are not yet derived from a complete theory, and it needs those corrections to behave stably under perturbations. A cyclic universe needs an entropy story that does not collapse into special pleading, and it must keep the cycles from drifting into a one-way expansion. A brain collision needs a higher dimensional framework with its own origin question, including why the bulk exists and why its laws are what they are. This is where the documentary connects back to Chapter 4's warning, because the warning was never just about mathematics. Singularities are alarms that our classical description has overreached, and the alarm rings when we push the equations beyond their jurisdiction. Replacing the singularity with a bounce or collision is meaningful only if the replacement is controlled by a deeper theory. Otherwise, we trade one unknown for another with better branding, and the mystery merely changes costume. So we ask what would count as progress on the central question, and we ask it in operational terms. If before becomes meaningful in a bounce, we must still explain the laws that govern the bounce, and why those laws select a smooth outcome. If before becomes a bulk time in brain models, we must still explain the bulk, including its stability and its initial conditions. If the universe is cyclic, we must still explain why the cycle exists at all, and why it does not unravel under entropy and quantum fluctuations. The ladder of nothing climbs again, and each rung is more demanding than the last. Empty space is not nothing, the quantum vacuum is not nothing, and a pre-Big Bang phase is not nothing. These models often reject nothingness outright, yet they force us to confront a deeper version of it. What is the minimal structure required for any cosmos to have a history? When we say, there was something before, we also say, there were rules before, and rules are a kind of existence. Now we pivot toward the climax with a constraint that cannot be negotiated. All these scenarios lean on quantum gravity, because the classical road ends near the Planck regime, where the very concept of space-time may change. The question of nothing becomes a question about the rules that make space-time possible, and about whether those rules permit a boundary at all. To ask what came before, we may need the theory that decides what before can mean. Next, we follow that demand into the frameworks that claim to quantize space-time itself, and we watch the familiar stage begin to dissolve. We ask whether geometry is fundamental, emergent, or replaced by something even stranger, something that only looks like space and time from far away. And we keep the hook alive, because the darkness before the first heartbeat may be not emptiness, but a different kind of law. Before the first heartbeat of time, our story reaches the place where stories break, and where physics begins to question its own language. We have traced the universe back through light, nuclei, and the oldest radiation, following evidence that still hangs in the sky. Now the road ends at a scale where space-time itself refuses to stay still, as if the stage shivers under the weight of its actors. General relativity treats space-time as smooth geometry, shaped by energy and pressure, with curvature telling matter how to move. Quantum mechanics treats fields as fluctuating, even in their lowest energy states, because uncertainty is not a flaw but a rule. Push both toward the beginning and their rules collide because the stage becomes part of the cast, and the cast begins rewriting the stage. The collision has a name that sounds like a promise and a warning. Quantum gravity is the attempt to unify quantum mechanics with general relativity, not by compromise, but by replacing both with something deeper. It is the search for a framework where geometry and quanta are not forced to coexist awkwardly, but arise from a single underlying principle. The reason is not aesthetic, and it is not optional near the beginning. At the Planck length, about 10 or 35 meters, concentrating energy into a region that's small would make a black hole in classical gravity. At the Planck time, about 10^43 seconds, the idea of a classical clock becomes unreliable, because any clock would disturb what it tries to measure. These numbers are not arbitrary milestones on a timeline. They come from combining the speed of light, Planck's constant and Newton's gravitational constant into natural units, as if the constants themselves are pointing to a boundary. At that boundary, quantum uncertainty and gravitational back reaction become inseparable, and the usual separation between system and space-time breaks down. In that regime, space-time cannot be treated as a fixed background. Quantum fluctuations should shake the metric itself, producing a superposition of geometries rather than a single smooth history. The singularity from classical equations becomes an alarm that the continuum approximation has failed, like a map that tears when you zoom too far. Visually, imagine the familiar grid of space-time lines from textbooks, straight and calm across the page. Now imagine the grid turning restless, cells swelling and shrinking, connections blinking in and out as if geometry were foam. Not foam in space, but foam of space, where here and there are no longer stable labels. This is where the documentary slows into meditation, without leaving physics behind. The central question returns in its hardest form. What do physicists mean by nothing before the Big Bang if space-time is not yet classical? When time is not a dependable coordinate, the word before begins to wobble, and the question becomes sharper rather than softer. Quantum gravity proposals do not agree on the answer, but they agree on the demand. The beginning is not just an early moment in time. It is the threshold where time, distance, and causality may emerge from something more primitive, something that does not yet look like a universe. Historically, this tension has been building for a century. Einstein's theory turned gravity into geometry, and it worked with stunning precision, from Mercury's orbit to the bending of starlight. Quantum theory, built in the same era, explained atoms, lasers, and the stability of matter with equal authority. The trouble is that each theory assumes what the other refuses to grant. Classical space-time on one side, quantum indeterminacy on the other. One path begins with string theory, where the fundamental objects are not point particles. The basic excitations are tiny strings whose vibrational patterns appear as particles and forces, like notes on a cosmic instrument. Gravity appears naturally as one vibration mode, which is why string theory is taken seriously, because it does not need gravity to be bolted on afterward. In this picture, the graviton is not guessed into existence. It emerges as an inevitable excitation of the string, carrying spin too and behaving like a quantum of the gravitational field. That detail matters because it suggests that quantum gravity might be less a separate add-on and more a built-in consequence of deeper structure. String theory also changes what we mean by space, because it requires extra dimensions. Those dimensions can be compactified, hidden at small scales, while leaving a four-dimensional world at low energy. The visuals here are deceptive, because the extra dimensions are not empty corridors. They are curled geometries whose shapes determine particle properties. The price is a vast landscape of possible vacua, each with different effective laws. Different compactifications can yield different particle spectra, different coupling strengths, and different cosmological constants, all consistent within the mathematics. The landscape sharpens an older tension from inflation and the multiverse, because abundance can look like explanation until it starts to look like evasion. If many consistent low-energy worlds exist, what selects the one we inhabit? The word nothing starts to look like a selection problem, not an emptiness problem. Even vacuum becomes less like blankness and more like a particular organized state, chosen from a menu that is almost unimaginably large. Another path is loop quantum gravity, which starts from general relativity's geometric language. It tries to quantize geometry directly, without assuming strings or extra dimensions, treating the gravitational field as something that can have quantum states. In this approach, areas and volumes can have discrete spectra, like energy levels in an atom, so that geometry comes in quanta. The discrete structures are often described as spin networks, graphs labelled by quantum numbers. They are not embedded in space in the usual way because they are candidates for what space is. A smooth metric becomes an emergent approximation, like a fluid description of molecules, valid when you stop tracking individual constituents. Picture a web of nodes and links suspended in darkness, each link carrying a quantum label, each node a junction of relations. From far away, the web blurs into a surface and then into a volume, as if continuity were a visual illusion created by distance. Up close, the usual idea of a point in space loses meaning, replaced by adjacency and connection. Loop-inspired cosmology sometimes replaces the classical singularity with a bounce. That possibility echoes the previous chapter, but the deeper claim is more general. The beginning might be a phase change in geometry, not a first instant, where a high curvature quantum regime transitions into a classical expanding spacetime. In that story, the Big Bang is not a boundary where equations stop. It is a boundary where the right equations change, like water turning to ice when the microscopic degrees of freedom reorganize. The question becomes whether the bounce leaves signatures in the distribution of primordial fluctuations, subtle fingerprints that a future survey might detect. Discrete ideas also appear in causal set theory, which begins with a different intuition. The core structure is a set of events with causal order, like a partially ordered network. Space-time volume corresponds to counting elements, and continuity emerges only at large scales, the way a coastline looks smooth from space. In causal sets, the fundamental ingredient is not distance but precedence. Who can influence whom is primary, and geometry is reconstructed from that causal skeleton. If that is right, then before the Big Bang could mean a region where causal order exists without classical metric notions, a kind of pre-geometric bookkeeping of influence. These approaches force a question that sounds simple and becomes unsettling. Is space-time continuous, as calculus assumes, or discrete, as quantum hints suggest? The answer changes what nothing can mean, because a discrete pre-geometric phase is not empty, but it is not space. Continuity has been physics' most reliable habit, because differential equations describe motion with extraordinary success. Discreteness is quantum theory's most persistent whisper, because energy levels and quanta keep appearing where we expected smoothness. Quantum gravity asks whether the smooth manifold is fundamental, or whether it is the large-scale limit of something granular. Now we pivot toward the climax with a constraint that cannot be negotiated. Any candidate theory must explain why classical spacetime appears so stable and smooth at accessible scales. It must also connect to the sky's data, including the CMB's coherence and near-flat geometry, because cosmology is not a playground without referees. The most dramatic shift in modern thinking is the idea that spacetime might be emergent. Emergent does not mean illusory, and it does not mean optional. It means geometry could arise from deeper degrees of freedom, the way temperature arises from molecular motion, real and measurable even though it is not fundamental. In this view, the Big Bang is not the creation of matter inside space. It may be the birth of the very concept of inside, because inside requires geometry. The question of before becomes a question about what existed when geometry was not yet a good description, when location was not yet a stable category. Holography is one of the clearest windows into this possibility. It begins with black hole thermodynamics, where entropy scales with horizon area, not volume. That scaling suggests a limit on how much information a region can contain, and it hints that gravity and information are entangled ideas. The historical shock here is worth lingering on. In the 1970s, Bekenstein argued that black holes must have entropy, and Hawking showed they radiate, giving them a temperature. Those results forced a new kind of accounting, because a black hole seemed to store information in proportion to its surface area, not its interior capacity. The holographic principle generalizes that hint into a radical claim. The physics inside a volume can be described by degrees of freedom on its boundary. A lower dimensional description can be fully equivalent to a higher dimensional gravitational world, even though our intuition insists the interior should be more real. In accessible terms, the boundary encodes the bulk like a complete ledger. The inside is not erased, but it is not independent. If the boundary data are fixed, the interior story is fixed too, as if the universe were a book whose plot is determined by its cover. This changes the meaning of before in a subtle way. If space-time is reconstructed from boundary information, then time and distance are derived quantities. The earliest phase might be described without any interior geometry, only by boundary correlations, and the beginning becomes a change in how information organizes itself. Holography becomes concrete in the ADS-CFT correspondence, where a gravity theory in a bulk spacetime matches a quantum field theory without gravity on the boundary. The boundary theory is ordinary quantum mechanics in one fewer dimension. The bulk geometry emerges from the boundary's quantum state, as if spacetime were a translation of entanglement into distance. We do not live in an ADS universe, and the documentary must not oversell the match. But the lesson survives the technical details. Geometry can behave like a code, and the code can live where geometry seems absent, an unsettling reversal of what we usually call fundamental. Entanglement is the bridge that makes this less mystical and more physical. Entanglement is a pattern of correlations that cannot be reduced to local properties, even when the systems are separated. In holographic settings, the amount and structure of entanglement can determine geometric features like distances and connectivity, turning correlation into architecture. A slogan captures the idea without proving it. Space-time might be woven from entanglement, with geometry as the large-scale bookkeeping of quantum correlations. If entanglement changes, the effective geometry changes, and what looks like tearing or connecting in space could be reconfiguration in information. This is not a metaphor that floats above equations. In holographic models, entanglement entropy relates to areas of minimal surfaces in the bulk. The boundary is information-theoretic quantities mapped to geometric quantities in the emergent spacetime, giving a precise bridge between bits and distance. Visually, we can imagine a dark field of points connected by luminous threads, each thread representing a correlation. As the threads thicken and organize, a shape begins to appear, like a landscape emerging from fog. The geometry is not drawn first and filled later. It condenses from the pattern of links. If geometry is emergent, then nothing before the Big Bang could mean a phase with degrees of freedom but no classical geometry. There could be a quantum state, a network, or an algebra of observables, while space and time are not yet defined. The ladder of nothing climbs to its most radical rung, where absence becomes a misdescription of unfamiliar structure. Now we test boundary ideas against what the sky actually measures. The early universe left a nearly scale-invariant spectrum of fluctuations, with phase coherence across modes. Any emergent spacetime story must reproduce that pattern, not merely reinterpret it, because the CMB is a fossil record with quantitative teeth. Those fluctuations are small variations in density and gravitational potential, stretched across the sky in a pattern that is statistically simple, but physically profound. They seeded galaxies, clusters, and the web of large-scale structure, making today's cosmic architecture a magnified echo of primordial quantum noise. The question is whether quantum gravity changes that noise, or only changes our interpretation of it. String theory offers one route through early universe model building, including brains and higher dimensional dynamics. It also offers holographic cosmology proposals, where a non-gravitational theory could describe an early phase. But it struggles with the landscape and with making unique, testable predictions, because too many consistent possibilities can dilute explanatory power. Loop quantum gravity offers another route. With quantized geometry and potential singularity resolution, it must still show how smooth spacetime and standard quantum fields emerge in the right limit. It must also handle perturbations with the precision demanded by CMB data, because small mismatches in the early spectrum can ripple into large disagreements later. Causal sets offer a minimalistic foundation, but they face their own challenge. They must recover local Lorentz invariance and the observed continuum behavior at accessible scales. They must also explain why the universe looks so homogeneous and isotropic on large scales, despite being built from discrete causal elements. Across these approaches, a recurring theme is symmetry and constraint. General relativity is built from diffeomorphism invariance, the idea that coordinates are not physical. Quantum gravity must respect that, while still producing a notion of time that observers can measure, because physics is ultimately about relations that can be compared. This brings back the problem of time from earlier chapters, now with sharper teeth. In canonical quantum gravity, the fundamental equation can be timeless, like a constraint rather than an evolution law. Then time must emerge as a relational concept, defined by correlations among degrees of freedom, like reading change off one subsystem used as a clock. If time is emergent, then the phrase "before the Big Bang" becomes a category error in the deepest regime. There may be no parameter that plays the role of earlier. There may be only a quantum state and a rule for extracting semi-classical histories, where history is not primary but reconstructed. Yet the documentary cannot stop at technical silence, because the central question demands a human translation. If there is no time, what does it mean to say anything exists? Existence becomes tied to structure and consistency, not to duration, and that is a difficult idea to hold without slipping into metaphor. Now the tension peaks, because the frontier forces a confrontation with the status of laws. Laws in physics are compact descriptions of regularities in what happens. But if there is no space-time yet, what are laws describing, and what does it mean for a law to operate without a stage? One answer treats laws as timeless mathematical relations. On that view, the laws do not need a universe to exist, because they are like truths about possible structures. The universe instantiates one consistent structure, and the laws are the relations that define it, whether or not anything happens in time. Another answer treats laws as emergent too, like effective rules that arise in certain regimes. On that view, laws are not prior to the universe. They are part of what comes into being when a universe becomes classical enough to display stable regularities, the way fluid dynamics emerges when enough molecules move together. This is not a purely philosophical fork because it shapes what we expect from quantum gravity. If laws are fixed and timeless, we search for a unique fundamental theory with minimal free choices. If laws are emergent, we search for mechanisms that produce robust, effective rules across many possible microstructures, and we ask why our regime is so stable. The cosmological constant problem returns here as a stress test. Quantum field theory predicts enormous vacuum energy, yet the observed dark energy is tiny. A quantum gravity principle might cancel, sequester, or reinterpret vacuum energy, but no consensus exists, and the mismatch remains one of the loudest clues that something is missing. Vacuum non-uniqueness returns as well, now as a warning about initial conditions. In curved, time-dependent backgrounds, the definition of the vacuum depends on slicing and observer. A complete theory should explain why the early universe picked the state that seeded the fluctuations we measure, rather than a different state that would have painted a different sky. Holography reframes vacuum questions in informational terms. What looks like empty space in the bulk can correspond to a specific entangled state on the boundary. Empty becomes a particular pattern, not the absence of patterns, and the word "nothing" starts to sound like a misread of a coded message. Discrete approaches reframe vacuum questions in combinatorial terms. The ground state could be a minimal network configuration or a highly symmetric causal order. Empty becomes a special arrangement of pre-geometric degrees of freedom, where symmetry plays the role that blankness once played. In every case, the documentary's hook becomes more precise and more disturbing. Before time could tick, the universe may have been described by information, networks, or symmetries. The stage might have been a code, and the actors might have been the rules of that code, rules that do not unfold in time so much as define what time can mean. This is the climax because it changes what we mean by birth. the birth of the universe might not be the appearance of matter in space. It might be the transition where a quantum description becomes classical enough to support geometry, clocks, and causal arrows, and where decoherence makes one history feel inevitable. The Big Bang then becomes less like a first event and more like a phase boundary. On one side, classical spacetime is a good approximation, and thermodynamic time has meaning. On the other side, there may be only a quantum regime where geometry is not yet defined, and where questions must be asked in a different grammar. We are not claiming a final answer, because the frontier is still open. We are naming the shape of the best attempts, and the price each attempt pays. The price is that nothing before the Big Bang may mean something stranger than any void, and stranger than any simple before. We end with a final tightening of the central question, now stripped of familiar scaffolding. If space-time is emergent, then before is not earlier, it is deeper. The last chapter must ask what kind of explanation is even possible at that depth, when even the word because may need a new foundation. Next, we step back from the frontier and decide what we have learned about nothing. We sort the ladder of meanings and admit where physics becomes inference, where it becomes speculation, and where it becomes silence. Before the first heartbeat of time, we asked what held reality up at all, and whether the word nothing could ever be literal. After 10 chapters, the answer arrives in layers, measured, conditional, and still unfinished. First, nothing in physics rarely means philosophical nothingness, the absolute absence of being, law, and possibility. It usually means a quantum vacuum. Fields still exist, their lowest energy state still has structure, and fluctuations are unavoidable. Even at zero, the vacuum seethes with uncertainty, virtual excitations, correlations, and a measurable pressure that shows up in effects like the Casimir force. Second, before may fail as a question if time begins with spacetime, because the grammar of causation depends on a clock. If there is no time parameter, earlier and later are not missing facts, they are undefined. General relativity already hints at this, because time is not a background stage. It is part of the geometry that can stretch, warp, and, in extreme limits, break our ordinary intuition. Third, some models replace a beginning with a transition rather than an origin. A bounce can trade a singular start for a prior contraction, while boundary proposals smooth the edge into a kind of geometric closure. Brain collisions offer another script, where what we call a beginning is a violent encounter in a higher dimensional setting. Yet none of these stories are confirmed. Now we step back from the frontier and sort what we actually know. The hot Big Bang is not a guess about creation. It is a tested account of evolution from a dense, hot, expanding state. We know the universe expands, and redshift turns distance into a time-ordered record written in stretched wavelengths. When we run that record backward with general relativity, density and temperature rise until the equations warn us. That warning is not a dramatic ending. It is a sign that a new theory must take over. We know the cosmic microwave background is real light from a real epoch, released when electrons and nuclei first combined into neutral atoms. Before that moment, the universe was a glowing plasma that scattered photons like fog scatters headlights. After a combination, the fog thinned, and the radiation streamed freely, cooling for billions of years into the microwave glow we detect today. Its near-perfect blackbody spectrum is a forensic signature of an early thermal bath, and the acoustic peaks are a frozen record of primordial sound waves. Those peaks encode the composition of the early universe, the curvature of space, and the timing of matter radiation equality. They are not poetic hints, they are numbers, sharp enough that small changes in parameters visibly shift the pattern. We know light elements were forged minutes after the beginning of the hot phase, when temperatures allowed nuclear reactions but not stable heavy nuclei. Helium, deuterium, and lithium abundances anchor the expansion rate and baryon density because the universe cooled like a stopwatch. Too fast and reactions freeze early, too slow and more fuel burns into helium. We know structure grew from small, nearly Gaussian primordial perturbations, tiny over and under densities imprinted across space. Gravity amplified them over cosmic time, pulling matter into filaments and nodes while voids emptied out. The same spectrum links the CMB to galaxies, weak lensing shear, and the sprawling cosmic web, one statistical fingerprint appearing in different eras. These pillars map our path back to early times with extraordinary confidence. as if data points were lanterns along a narrowing road. They do not tell us what happened at the Planck boundary, where quantum effects of space-time itself should matter. They also do not tell us whether happened applies there, because our best-tested language may stop being meaningful. Now we name what remains open, without disguising it as mere detail. Inflation fits